But I would like to welcome you here, both to our online participants and our in-person participants, to the Quantum Autumn School 2024. And it's my pleasure to do this again now together with NordIQuEst. You will hear from Alberto here in a while. And I also want to thank our various funding sources that have also made this possible, our support action Castiel, and also the Nordforsk organization. So my name is Tor Wikfeldt. I'm the director of ENCCS. We are the National Competence Center in HPC as part of the EuroCC project. This is the second time we do the Quantum Autumn School. We did it first time last year, QAS 23, in Gothenburg. Some background noise, that's okay. Yes, and so this is the second time, and you might be wondering why we call it the Autumn School when it's already December. Well, it was a multilateral collaboration, and we just didn't find a week that suited everyone until December. But the good news is that the weather is sort of autumny, at least in Stockholm. Okay, we have a really exciting program ahead of us. I'm now scrolling just through the event page. This is today. We will have an opening talk by Sven Karlsson in a few minutes. And then, well, you can see for yourself this afternoon, we get an introduction to the quantum computer that we'll actually use for this autumn school, Helmi. Tomorrow, more theory, more hands-on, several interesting types of use cases, and then even more on day 3. So this is our project, right? We belong to RISE, Research Institutes of Sweden, and also Linköping University. So we split over these two. You might have heard about us in many contexts. Maybe this is all a repetition, but we're HPC experts. We provide training like this one.
Can you check it now?
We help you get access to HPC for free. So if you have unmet compute needs, regardless of whether you're from academia, public sector, or industry, get in touch with us. We have all kinds of good stuff on the website, success stories, tutorials, a podcast. So subscribe to our podcast. You can find everything on our website, enccs.se. And I will welcome also Alberto to introduce himself and NordIQuEst.
Thank you. I'm Alberto Anzanova. I'm the project manager for NordIQuEst, which is a very short acronym for a very long name of a project. It's the Nordic Estonian Quantum E-Infrastructure Quest, basically. So a very long name. We are a NAIC-funded project. It's a Nordic E-Infrastructure collaboration. So we are a consortium from the Nordics. We basically put together different organizations across the Nordics. From Finland, we are CSC, the IT Center for Science, VTT, the Research Center of Finland. There is then Chalmers Next Labs here in Sweden. And we have the Danish Technical University in Denmark, University of Tartu in Estonia, and in Norway, SINTEF, and Similar Research Lab. So this is a little bit the key of our project. When it comes to quantum computing, we realized that each country cannot do that by themselves. We have to pull together resources, that it comes down to both hardware, but also people know our expertise. So I'm really happy. And I think that the Quantum Autumn School, it's kind of a good comparison from this point of view. We are different organization and we are putting together different expertise and trying to provide participants with a good experience. So thanks to everybody that is involved today, and thanks to Tor and your team for really coming back with an offer I couldn't refuse this year. Because it's the second time in a row that we are doing this. So I'm really, really happy about that. Regarding NordIQuEst, we are a relatively small project just in the Nordics, but with big ambition. One of the main objectives is to build this infrastructure between connecting HPC center with quantum computer. And according to our information, our research, we were basically the first one, academic project, to actually connect a quantum computer located here in Finland, CAL 9000, to a supercomputer, Lumi, in the north of Finland, in Helsinki, basically. And that happened a few years ago already. So I believe and we think we are the first one to do that. And this infrastructure is something that you will use in the next few days as well. Basically, you will access from here in Stockholm or wherever you are online, from your laptop, Lumi, the supercomputer. Well, it's not anymore the fastest supercomputer in Europe, but still in the top 10 in the world, in Kajaani. And from there, you will access Helmi, the quantum computer that is in Espoo. So from Stockholm to the north of Finland to the south of Finland in Espoo. So this is something that will happen. So I'm really happy to see many participants both here and online. And this is the other aspect of the project as well, because alongside pulling together the resources to create this infrastructure, we also want to influence the future of the quantum computing in general. So we're really happy and we really believe that this kind of events together, as we said, with different organizations and also from the industry, we want to foster the growth also of the knowledge of quantum computing, generally speaking. So I really hope that you will enjoy the next 3 days of quantum computing. I hope you will have fun. I hope it will be somehow also inspiring and, well, have fun. So thank you, everybody.
Okay, so with all the necessities covered, let's welcome our first speaker, Sven Karlsson from DTU in Denmark.
All right, thanks so much. All right, thank you, Thor, for a very nice introduction. I'm Sven Karlsson. I'm a professor in high-performance computing systems at the Danish Technical University, but I'm also a work package leader in the NordIQuEst project. So I would like to take some time here until lunch, and I do appreciate that you're eagerly waiting lunch, so I will do this as painless as possible. To talk to you a little bit about the integration of high-performance computing and quantum computing. And this is really the key topic that we have been addressing in the NordIQuEst project. So you can also see the NordIQuEst logo type on the bottom here. You'll probably see it several times throughout the session here. So perhaps start by talking a little bit about, I'm an HPC person, and why do I think quantum is interesting? Well, quantum adds something interesting to the field of quantum, to computing. It adds and changes what fundamentally is computable. So if you're looking at what we can do with classical HPC, we can do a lot. I'm one of the persons that tend to say that always that HPC is the single most important thing in the universe because it helps us to solve the key societal challenges that we see around the world. But with a classical computer, we have limits to what we can do, and quantum adds additional capabilities on top of that. I'm sure that everyone in this room knows who Richard Feynman was. If not, he was a very famous American physicist from 60s to the 80s, roughly. He was essentially a media superstar, and he was invited to talk shows and all these kind of things to discuss quantum. To discuss physics. And he noted in 1982 that for some physics problems, you actually need to use a quantum system because the physical system is a quantum system. So he essentially hypothesizes that we would need another type of machine. The regular classical computers would not be enough for everything, so we need something on top of that. And this is what we are on the verge on slowly but steadily getting to. So essentially, by adding a quantum computer to an HPC system, we can actually solve problems that we couldn't do before with a HPC system. And these are problems within chemistry, within optimization, various other things. I'll give you some examples throughout my presentation. But as you will see throughout these 3 days, you will also see a lot of interesting discussions from various companies and various other researchers. You see more fully what kind of problems you can address. I'm also an HPC researcher doing research on the fundamental technologies involved in HPC. And as many of you know, Moore's law is ending. We will not get the speed boost that comes from Moore's law anymore. And with that in mind, quantum computing also allows us to get another type of accelerator beyond GPUs and other types of accelerators that we may have heard of. And quantum computing provides a promise to go beyond the scalability of our current system. And I think there was a question. Please go ahead. I'm not sure whether I can throw this at you, but let's see what we can do.
Haven't people said that Moore's law is ending for a good while now? And when do you think, when do you see that happening in HPC and outside of HPC, I suppose? Because I guess it's a very important breakpoint for quantum computers, right?
Right. Yeah, so I think it depends on where you are in the technology nodes. I'm not now talking about circuit design, right? So bear with me. Not every one of you are a physicist or inversed in circuit design. I think when you go to 3 nanometers and beyond, we see that transistors consistently becomes worse. Which means that, yes, your transistors may become smaller, but we also becomes worse, right? And here's really where we see that Moore's law is really ending. And I think there were a couple of American companies claiming that, well, we can continue with Moore's law for some time. They are now saying that, well, sorry, we were wrong. This is ending. So depending on where your product is and when it comes to market, you will probably still see some evolution. So let's say if the extreme scale, high performance scale, we already see this. We see a stop. Probably we have one more generation of processors, one more generation EPUs becomes really painful. If you are in the better market, it will take a couple of generations because they tend to trail a little bit in the technology. But once they get down to the feature sizes I'm talking about here, then they also see this stop. So unfortunately, we tend to say we used to have a free lunch, we don't have that anymore, and that's something we need to also adjust to. And quantum allows us to probably push further, which is interesting. Did I address your question? We can also have an offline discussion at lunchtime if you want. Another element here is that quantum computing is actually quite radically different from classical computing. We need to think fresh and new about algorithms. And this has actually led to new classical algorithms. So quantum has challenged the classical domain, and you've gotten better and better algorithms as a consequence. So we also see sort of in a way, a discussion back and forth between quantum and classical. And those of you that have followed these claims towards quantum supremacy that some groups and companies have made us probably also saw that pretty soon after a quantum supremacy argument has been made, someone will come up with a better classical argument to allow you to actually push forward in the classical domain. Okay, let's move forward here. So we expect you coming into this autumn school to actually have a basic understanding of what quantum is and gates and things like that. If not, I do encourage you to follow the primer that we linked to, and some of you perhaps also follow the IQM webinar the other week. Of course, I don't expect you to read up on that immediately, just to take you through this. This is a so-called circuit diagram. From left to right, we have different types of gates that are applied to these horizontal lines, which describe something called qubits. And this is one way to describe algorithms for a quantum computer. Those of you that are familiar with digital design, this is actually quite similar to a digital circuit, and then actually you can reasonably well transform a digital circuit into a quantum algorithm with some caveats. Those of you that are familiar with digital design may know of a full ladder. This is the quantum equivalent of full ladder. Does the same thing as a full ladder with some, again, some caveats I'm not going to go through. And this is how most quantum computers are programmed, and then you will play with this during the labs later on. Now, the gates are largely technology independent, similar to in digital design. The actual implementation of these gates are technology dependent, and there is a mapping step that tools need to do to go from the sort of technology independent gates into something that the quantum computer can understand. And this requires tooling. And why I'm bringing this up? Well, not only do we see quantum computers as accelerators to HPC systems, we also see a role for HPC systems to make the tooling for quantum more effective, at least when, and certainly when we start scaling the quantum computers upwards. There are a couple of key algorithms in the different technology mapping steps that are actually NP complete. Those of you with a computer science background probably take notice that this is getting difficult, right? And we see a huge advantage of using HPC systems to actually push the boundary a little bit, what we can do in terms of actually mapping, at least realistically, optimally, gates towards the quantum computer. Another thing that is also part of this mapping step is that, I'm coming back to this later, quantum computers are essentially analog devices, and in order to control them, you need to push analog pulses or modulate light and other ways to send analog information into the quantum computer. And this is also where we see that this is part of the mapping step, but also optimization of these kind of pulses is something that we see that HPC systems can do. And especially as we both get faster quantum computer and large quantum computers, we see a need for more compute power for this step. And then as you all know, there is now a limit on how large algorithms we can make because of the fundamental technologies we're using for quantum computers are in the so-called NIST stage, where we don't have reliable gates, we don't have reliable qubits. Essentially, information survives for a short period of time, and within that period of time, we can do some work, right? So let's now dig a little bit further into the interplay between quantum computer and HPC. As I said, from HPC perspective, we see quantum computers as accelerators these days. So we do expect quantum computers to be co-located with larger HPC systems. This is what's happening around Europe, around the world, also in the Nordics. Coming back a little bit to that later on how that's done. And we see a number of these quantum computers being fielded. They are now becoming useful and usable. And we see an active ecosystem development. And as you are bearing witness to, there is actually quite high demand from users to play with these systems in various forms or fashions. I can give you one example that I'm not sure I'm at liberty to say what company it is, but there is a French company in the energy sector that are buying their own quantum computers right now because they feel that that's necessary for them to stay ahead of the technology curve. And we see a lot of the same kind of mentality from various kinds of companies that either they're buying their own machinery or they are very much invested into having their own internal scouting activities for quantum, because they see this as also important for the future. We all agree, at least from the HPC side, that we see an interplay between HPC and quantum. We require some quite complex software systems, in some cases also hardware systems, to make the quantum systems work. As those of you that are interested in hardware, I can mention that right now there is one new quantum computer being fielded in Germany, where you actually attach the quantum computing over a PCI bus to a host system. And this is actually quite recent development. Before, you had quantum computers connected over some REST API or web interface, but now you actually start integrating quantum computers at a very deep hardware level. We also believe, and I think now we see this being embraced across all kinds of organizations and companies, that the applications that you see for quantum are going to be hybrid, where you have one component on the classical side and HPC side, and then you have another component that is the accelerator side, the quantum side, right? Where the quantum system does what the quantum system does best, and the HPC system does what the HPC system does best. And there are some mature activities on this. We have NordIQuEst, as we already have been introduced by Alberto. There is also other activities in Europe, at least very, very strong in the Bavarian area and around Munich. And here I'm very proud as European to say that Europe is actually at the forefront. Europe is significantly ahead of Asia and the US on this, with a potential outlier in China, because China is not telling much about what we're doing at this stage.
Yeah, I'm curious. I'm happy you're saying this, but how exactly is Europe ahead? And maybe if you can quantify that.
Right. Yeah. So we can see that, as Alberto mentioned, we made the first integration of a quantum computer and a HPC system already back in several years ago. Japan is now starting to do that, and the US has not quite done it yet. So we have several years in terms of the tech curve ahead.
So thank you. So you mean we're ahead in the specific of integrating HPC?
Exactly, that's correct.
Computing. Okay, so a follow-up question on that. I spoke to someone in the States, and they seem to be placing lots of bets on networking quantum computers and building entanglement-based networks,
right?
Rather than, I heard that as sort of an alternative approach. What is your take on that?
I mean, I fully agree, and we have plenty of activities in Europe that does this as well. So there's one project in Finland I know of. I'm not familiar with if there is anything in Sweden. There is a European project that does that. And we see across the board a lot of interest to connect the quantum computers up. There is a bit of a caveat to my knowledge. You put some limitations on what technologies you use. Ion traps modulated by light is easier to connect up, because then essentially just the optical interface, and light can be transmitted for several kilometers over a optical fiber and maintaining entanglement, right? For other systems, it's more difficult, because typically you need to move from a pulse to light and to be able to transmit. But there are people looking into this, see how you can make entangled or pseudo-entangled type of information being transmitted. However, there is another thing that I didn't put it part of my slides, but I'm bringing it up because I got this question. There is a lot of effort going into so-called circuit cutting, where you're taking a large circuit and try to figure out, essentially using graph theory to figuring out how many qubits do you actually need for this type of, for this central computation. And then you extract that circuit out of a larger circuit. And in many cases, you can actually fit a large circuit onto a smaller machine because you don't need full superposition, so it's full entanglement across all the different qubits. So there are some limitations to this, but we see a lot of interest and a lot of good results from actually taking a large circuit, cutting down smaller pieces, running them independently on a quantum computer, and then sort of stitching together results. So that can also be done. Then again, we are seeing a lot of larger systems being fielded. I believe the largest machine I know of have 150 qubits, and that's in Germany. That's been fielded, connected to an HPC system, and we also see other larger systems being brought up. Of course, this is a moving target, right? One very promising technology is neutral atoms, where we can probably scale up to thousands of qubits relatively easily. And again, if I would be happy to go into detail during the break. So what are the general challenges that we're working with in HPC QC integration? So let's start with the top line and work towards the bottom. Things are changing over time, but going back just 2 years ago, quantum computers was something that looked very much like a physics experiment. No offense to the physicists, but they were not really productized. So you can really see that this is something that was a standalone, that worked as an experiment, and that's fine. All credits, it works, right? But there is a bit of effort here to move that into something you can start integrated with other products, but also integrate into other quantum computers, as we discussed earlier. This is something that's ongoing, and at least both from the physicist side, but also from the quantum computing side, there was a bit of learning curve to understand. So, what is a HPC system? How does these things work? What do they need to do in order to integrate fully with HPC system? HPC systems have a very matured software stack. That's something that likely is not going to change. We can adapt. So here is clearly that the quantum computers has to adapt, and that has happened over time. We're not quite there yet. But we're moving towards having a single system with quantum computers as accelerators. Related to that, we have several software stacks here. We could even have several software stacks within a single quantum computer. And this, of course, has to be changed so that you have a single uniform software stack across the entire system, but also more importantly, perhaps, a single way to program these kind of things. So again, quantum computers early on has been something that came out of, I would say, physics labs, where they have tried out different ways to program. Now we need to merge these thoughts and abstractions into what we do in HPC, and this also is happening, but it will take some time further. The second item here is something that's very, very much research. The first item is perhaps more towards the companies involved here to produce the right product. This is essentially productization. The third item is that, and this is something I witnessed firsthand, that integrating a quantum computer physically into a data center is not a simple thing. So if you look at the spec sheets for quantum computers, they often say, okay, you need a temperature drift of 1 degree. It should be 25 degrees or 22 degrees, something like that. Should be not a lot of vibration. It should not have a lot of noise. Should not be a lot of EM fields and things like that. And I'm not sure how many of you have been in a data center. Quite some of you. Yeah. So a data center these days could be 50, 60 degrees, right? At least in some places. It's noisy. It's really loud in there, right? I wear hearing aids or hearing protection aids whenever I go into data center, right? Even though some people are not, but I do. And everything is vibrating. There are fans. Everything is moving around, and of course, EM fields everywhere. There were plenty of quantum computer companies that for this was a rude awakening, realizing, okay, this is how it is. So they had to actually redesign the systems, had to work a lot with it. You have to understand sort of how, what are the limits, what can we do, what can we do. There's also a lot of things we do in data centers that quantum computers has not been thinking about. So for instance, we monitor everything in the data center states, all right? So we put sensors everywhere. An HPC system is a very large IoT system, really. You have sensors everywhere. You have, if you have water cooling, you have flow meters everywhere. You have temperature meters everywhere. You measure vibration. You may measure fields, all these kind of things, and we collect all of that. And we also started to ask the quantum computing people to give us information about things, right? So we like to give you sort of what kind of EM field do you measure in your cryostat? What kind of vibrations do you see? What kind of temperatures do you see over time? All these kind of things, right? And they also had to adapt to this. So this took some time, but we're moving towards that. The final aspect here, which I find is really interesting, I have a dirty little secret that I tend not to tell too often. I have a master's degree in physics. And that's helpful when you're working with quantum computers sometimes. I've been in meetings where people have been shouting at each other because they have misunderstood what they meant by a single world, right? So I wish there was, those of you that are familiar with British comedy, I wish there was a Babelfish or something like that to let people understand each other here, because this is, for many years, this has been an issue, right? So what we see here is that we have various domains, computer science, I'm probably from that. We have math, we have electrical engineering, we have physics. There are different communities, they have built their own nomenclature, their own kind of sort of references. Now we need to merge these worlds of people together and make them understand when they say, when I say X as a word, this is the definition, this is what I mean, and they have to learn to say that. For a computer scientist, a simulator is a very specific thing. For a physicist, simulator is also a very specific thing, but it's not the same thing as the computer scientists say it is. So very simple things, right? You have to be very upfront and say, you know, okay, this is what I mean. And it's taking years here for people to actually talking together very fruitfully. And I think this is also what we have been very successful with in the NordIQuEst projects. We actually have various different types of people with background here coming in and actually started discussing with each other. And it has been painful. We have had workshops where days have gone because we just were fighting through, sort of trying to understand each other, and after a while we started to understand each other, and it was then we were very productive. But we also see now that across the community, we are now coming towards a hybrid HPC QC community where we actually can start talking to each other. We have actually master programs being started, one in Denmark, but also in other places around the world, where you actually bring in bachelor students from computer science, from math, from physics into a single master program and have them work together and give them courses where we actually address this and say, you know, this is the definition we're going to work with. This is the definition we'll work with again, and see how we can use that to form and shape things. And we have plenty of events like this, but also globally where people are talking about this, coming from different backgrounds, talking about this in a very constructive way. So there's a lot of open challenges here. From a computer science perspective, we have software, we have workflows, we have the operating systems, we have a hardware, etc., etc. So just let me take you through here. Perhaps to dwell a little bit more into the technology stack we have with quantum computers. So I'm just going to take you left to right, top to down. So at a very high level, we have various forms of theory models. These essentially mathematical models about how we can express information, right? So these are then typically transformed into algorithms, usually described as a gate model, as I showed you earlier, but it could also be described in other ways. And here you also need to take steps. There are possibly tooling involved. Once you have the algorithm, you need to map the algorithm to quantum gates. There are various types of quantum gates. Not all quantum computers implement all gates. So you may want to take sort of high-level algorithm and map it to the type of gates that a quantum computer actually leverages. Then based on that, you then put together a quantum circuit, right? Now, the next step is to map that quantum circuit into the control unit of the quantum computer. The quantum computer is nourished by a small-scale HPC system, usually in form of a rack, so 19-inch rack, yay high, standing next to the quantum computer, having various forms of equipment to cradle and nurture the quantum computing. And this is usually called the control unit. And it takes the quantum circuits and transforms it into control signals for the quantum computer. Here's also a mapping step where you also need quite aggressive algorithms to do this. And then on the right-hand side, we have the actual quantum computer where you have low-level control, where also here you have algorithms and hardware that's involved. You have control loops. Those of you that are good with control free, yay, you have a new application area for your work. The quantum computer can be seen as a controlled system. There's software running it to keep it in operations all the time. And then you have the actual quantum chip. So
I'm hearing that any quantum algorithm can be implemented, at least in theory, not just on a circuit model or a gate-based model, but also on a measurement-based quantum compute, which is, I guess, a different model, right? In this scheme. Where is the sort of, is it possible to say how that changes what's on the screen here? Or where is the abstraction level where a circuit-based or a gate-based model is different from a measurement-based model?
It really changes in the mid. So I would say it's only the quantum circuit that's different. So in measure-based systems, you using the measurement theory to implement gates indirectly. So a quantum algorithm is reversible. And the only way you can actually get result is by measuring. In measurement systems, you can measure in different ways, and by doing that, you can then implement something that looks like a gate. So if you look at this, the quantum circuit is different, and then control unit is controlling the measurement system. The rest is the same. The top level is the same. But you still need tooling to map from sort of your high-level abstraction to your measurement-based abstraction. And then, of course, there are some people that are working on the left-hand side, top side, in the information model, and the mathematical side, using measurement as an abstraction, right? And then they can actually sort of shortcut some of the steps. But other than that, the stack is identical, I would say. I would say that most measurement systems are optics systems, and there's still a lot of research going on. I'm not fully up to speed with that research. I would be hard pressed myself to say that they are fully universal at this point. There are several optics-based systems that are simulators that can do a limited amount of programmability. That I cannot fully see. I'm not sure whether you can argue that they are universal, but again, I'm not fully up to speed with the research on this. All right, in terms of time, I think we can skip this. I already talked about that. So I'd like to come back and also mention here that we have quantum computers. I mentioned that earlier. I'm coming back to this now. We have quantum computers and accelerators for HPC, but we also have HPC as an accelerator for quantum. So what do I mean by that? So across all these different steps that are on the slide here, we have a significant amount of compute that will do the transformation. And many of these steps, again, are NP complete. You have approximative approaches. Sometimes you need to use things like SAT solving that are very, those of you that are in optimization knows about SAT solving. It's a very, very computational heavy approach, but it gives you good results. And we see that the computational heavy approaches are necessary for good quantum results. So we see as quantum computer scales, we actually need more and more classical machinery in order to run the tooling, right? And it's across the board. It's from mapping from the high-level theory to algorithm, to the gate sets, to the circuits, control unit, and then onwards, right? Also on the low-level control, where we also see that for something like fault tolerance, we're coming back to that on day 3, I believe. Or it's tomorrow, fault tolerance, right? Tomorrow morning.
Fault tolerance, when do we have fault tolerance?
That's tomorrow morning, right?
Error correction, yes.
Yeah.
I believe so.
Yeah. So where we see actually the way that we need significant amount of compute power to nurture the quantum computer and implement error correction. And that is a necessary step for fault tolerance. So across the board here, we see that classical computational resources are necessary in order to have a working quantum computer. And we see the demand for classical HPC resources just grow as the quantum computers grow. So let me also take you here in the last 10 minutes through the NordIQuEst. NordIQuEst is something we put together now several years ago to actually be proactive about these kind of challenges I outlined. So what we would like to do is put together a set of interfaces that is actually corresponding to a software stacks. We were not entirely sure we would be able to do a full software stack. In the end, we could. We wanted to put together various forms of libraries with examples of algorithms. I'm coming back to that in a moment as well. We wanted to produce training education material, and we wanted also to have an ongoing discussion with users here. And we also identified that in order to do this, we need to work together. And we found it natural to work together across the Nordics. Number of the partners already have been working together in various forms of fashions before. Several of the partners already had quantum computing infrastructure. Most of us had HPC infrastructure and want to see, can we now start putting the pieces together? So we started our sketching a software stack from what we had available. Probably today we will have drawn this slightly differently, but it worked well throughout the project, where we have quantum jobs at the top level. We have various forms of programming models. We decided not to implement our own, but use existing ones such as Qiskit and Cirq. Feeding into a middleware that allows us then to run these quantum jobs on top of a quantum computer. We also had simulation of circuits into the mix here. We also looked into what we felt was important. We needed some trailblazing activity in terms of how do we deal with users. So why is that important? We have an HPC system that is operated potentially by one organization. We may have a quantum computer operated by another organization. If a user were to transfer from one domain to another, we need to map users across the domains, these kind of things. That's difficult. And that was actually a large portion of the project to make this work properly. I think Martin, you can attest to that this is not trivial. Martin is sitting in the middle there. He's one of the key actors in making this work, also together with our good friends in Estonia. So essentially, we had an understanding of how we can make a rough, perhaps skunkwork-ish type of integration of HPC and QC, so we can learn from that. And we did that. And we are towards the end of the project, and we feel that we are really successful. We managed to implement all of this. Actually, very early on, so 30th of March, as Alberto mentioned, on 2022, we ran the first job where we had an HPC program running a quantum algorithm onto a quantum computer. So this was a full pipe cleaning experiment where we were able to run. We submit an HPC job onto the HPC system. The HPC system, the program running on the HPC system wanted something to run on a quantum computer as an accelerator. That was sent off to a quantum computer. The result was sent back and analyzed by the HPC program. So this was not sort of a mock-up in any form, but this was an actual working solution. And you will actually also be seeing some of that throughout the activities here. And this was, to my knowledge, and I think what we see worldwide, people tend to agree this was the first time this was done. And then we built on top of that throughout the project.
Sven, I'm wondering if I can bring up an interesting question from the
Absolutely.
shared workshop document here. So last week, DeepMind's Demis Hassabis said that AI might be able to solve problems that quantum computers were supposedly necessary for. Indeed, he said that classical systems, AI run on conventional computers, can model quantum systems. What's your take on this? Challenging question.
Yeah. Can you repeat or?
Yeah. So Demis Hassabis from DeepMind said last week in unknown context that AI might be able to solve problems that a quantum computer were supposedly necessary for.
Yes, I think that is probably true, but you also have to understand that AI is an approximative method, right? I mean, the way we currently develop, at least what people generally call AI. You also have the full AI that people were exploring in the 60s and in the 80s. But currently, essentially AI has been uniformly equal to using various forms of neural networks, right? And a neural network is an approximator of a unknown function, right? So yes, there has been work where you have had using neural networks to, for instance, explore various forms of solving Schrödinger equation and things like this. But doesn't necessarily mean that you will get the full Schrödinger equation solution. So I think you can get far with AI. I'm not sure you can get the full solution with it.
Yeah. Are you ready for more questions, or shall we take them at the end?
I would be happy to have questions coming in whenever you want.
Yes, so they're coming in the room, but also online. So another one: why is it not possible to use existing job scheduling systems like Slurm to submit jobs to a quantum computer?
Right, that's a very good question. It's also, then I can skip some slides later on, so the same time. Slurm makes a research allocation essentially in one step. And typically what we would like to do here with a quantum computer is that when we're executing a HPC program, we would like at various points in time to ask for a quantum computer. So at each of these steps, we will then have to rerun Slurm for each of those steps, and that's something that's going to be extremely heavy. Slurm is also resource demanding system. So essentially what we are looking into are multi-level scheduling approaches where you schedule HPC resources in one way, and then you schedule the quantum resource in another way in order to save computation time, essentially, for the scheduler. I think technically you could potentially do it with Slurm, but it's going to be way too much overhead, simply.
Yeah. So there are more questions, but we can wait with them perhaps until.
All right, that's fine. That's fine. Another thing that we developed in the NordIQuEst project is an application library, as I mentioned. So this is a very practical approach. We want to document and collect curated material. So this is on quantum algorithms. It's on examples of use of quantum. It's also experiences with quantum. And also for different types of use cases. And the way we put this together was that we collected both practical and theory aspects. Because if you remember, we have this very high level mathematical information theory aspects that are important to collect. And then these are transformed potentially into algorithm later on, which is perhaps more practical. So we want to collect both of these into our application library. And we also wanted to have various forms of Jupyter notebooks and code available that people can look at and play with and also actually download and work with. This is available online, so you have the link there, NordIQuEst application library. It's also on GitHub. So you can clone GitHub, you can get all the information there, and you can also add things. And we definitely want to see your pull requests. So if it's something you would like to contribute or something you see, okay, this is wrong, you probably have made a mistake here, let us know. Fork the library, send us a pull request, and we'll address it. So just to get you through one example in quantum chemistry here, we have, as an overview, what example we have the complete software requirements. What do I need to install on my machine in order to run the example? You have the theory in terms of both in the problem domain in chemistry, but also in the quantum information theory domain. So what is the chemistry problem we are solving? How do I leverage the quantum information theory as elements in order to implement it? Then we also have a work list, full work list. So what are the steps involved? How do you run them through? So for example, if you want to replicate for another chemistry problem, you can look at the work list, say, okay, these are the steps taken. I can leverage that to understand more carefully what the people are doing here and how can I adapt that to my own problem. And then we also have a full notebook for you to play with for this example. On the right-hand side, you see a small snippet here with some of the Qiskit code for that example that you can see in the notebook. So these are kind of curated examples we have in the application library that people can learn from, but also use to develop their own applications. So I think I'm quickly going through towards the end here. Now we should be coming up again, I hope. There we go. All right, I just want to take you through some of the initiatives that are happening across the world, right? I mentioned NordIQuEst on the left-hand side. We also have in Europe coming up projects. One is LumiQ, which is also the Nordics are all involved in. In the Bavaria, we have the Munich Quantum Valley, but also globally we have in IEEE, now starting also a quantum HPC working group where a number of different topics are being discussed. So I think in particular, if you're interested from a industry company perspective, the IEEE Quantum HPC working group would be quite relevant to engage in and build a community there. So with that, I think I should stop. I overstayed my welcome here a little bit. Sorry for that. We also had a lot of good discussions. I'll be around at least until lunchtime tomorrow. So we can certainly have follow-up discussions offline. Are there any pressing questions that we'd like to address from the chat?
There are many very good questions in the chat, but I think we should answer them. I mean, we should have lunch, and we should try to answer all these questions by text in the document. So maybe I'll ask you, Sven, and also other experts in the room to have a look. And these are definitely questions worth answering. But let's thank Sven for this really interesting presentation.
All right, then. Hello, everyone. I'm Zuhair. I'm from VTT, and I'm a research assistant in the quantum algorithm and software team. And I'll be giving everyone the introduction to Helmi. So first, let's actually start with what Helmi physically is. Now, it's a superconducting quantum computer, and it is currently in-house in in the VTT premises in Finland. So it is a 5-qubit superconducting quantum computer. And as you can see, it's in a star-shaped topology. So you have a central qubit, and then all the other qubits are connected to it. And this was jointly developed by IQM and VTT. So it's very much a prototype. And it has like tunable transponds for our qubits. And then these, you can do 2-qubit gates using the tunable couplers. And I guess this is a bit outdated at this point, but Helmi can be accessed through CSC via LUMI, Europe's second fastest supercomputer, and we will end up doing that just in a short bit. So when you actually need to run things on Helmi, we have a native gate set here, which is the phased RX gates. So just as a short description, I hope everyone is familiar with the block sphere. And with the block sphere, what you can have is, so with the block sphere, what you can have is essentially this equator where the X and Y axis is, and you can rotate around any line on that equator. So that's the phased Rx. So you can essentially have your rotation around the X, and then you can phase that around by an angle phi. And then for our 2-qubit gates, we natively support control Z gates. So this is, for example, different from how IBM does it, which is control X gates. And we perform measurements in the Z basis as a standard. So you'll get zeros and ones. And you may be wondering about how we do Z gates. So we do virtual RZ gates using the control stack. Essentially, we just modulate the pulses, and we apply the phase through the software rather than through the hardware. And this has been shown to produce better results. Now, as I did mention, Helmi is very much a prototype, but even without that, it is a 5-qubit quantum computer in today's world. So it is very much a NISQ device, a noisy intermediate scale quantum computer. And so what that essentially means is there will always be noise, there will always be errors, and there will be some things there will be some specific ways that we can mitigate errors on NISQ devices, and we'll cover a few of them, but we'll specifically cover the ones that are more useful for Helmi, because these vary based on the exact quantum computer you're using, the type of quantum computer, everything. Okay, so coming to errors in NISQ devices, you can see already we have the single qubit gate fidelity over here, and then the readout fidelity. These are the data from just a few days ago. And you can also see to the side, for example, what this CZ gate fidelity is. And you can see, for example, qubit 4 is pretty bad for both of them. That's changed in the last few days. We'll see, because as a NISQ device, one of the other issues that you can have is it's not very consistent. The way that the device acts will always change. So first, let's look at the simplest circuit we are going to run. So this is going to be a 5-qubit G8Z state. So if you're familiar with, let's say, the bell pairs, then this is essentially extending bell pairs over to all 5 qubits. So I hope everyone's familiar with this, but let's quickly run over. So first we initialize the circuit to all zeros, and then we apply a Hadamard on qubit 3, which, if we remember, that's the central qubit, and that's the one that's connected to all the other qubits. And once we have all the other qubits, then we can slowly apply control NOT gates. And then finally, we perform measurement. So ideally, we should only get all zeros and all ones in equal proportion. And this is a general, it's a pretty easy way to get a quick indicator of how well your quantum computer performs based on what's the largest G8Z state that you can create which has a good enough fidelity. So usually you want fidelity at least 50%. So let's start by preparing a 5-qubit GHZ state on Helmy. So over here, if you have a look, you can see that we have CNOT gates, but that's not exactly what we end up using. So Helmy does not support CNOT gates. So we have to break this down. So we can convert the CNOTs to CZs. And a Hadamard gate can be broken down into RX and a RZ gate. Sorry, does someone have a question online? Okay. So yes, we can decompose the Hadamard gate to our native gate sets, so the phased RX and the RZ gates. And since we measure in the Z basis, we can optimize some of these virtual RZ gates away. And so this is the actual circuit we'll end up running on Helmy right now. Okay, so I hope everyone knows how the Lumi access on demand works. So if you go to the Quantum Autumn School and then come to content, and I'd recommend everyone runs along over here.
I think we need to give plenty of time to this particular step.
Yes, yes.
Yeah.
Okay.
So everyone is now supposed to run Lumi open on demand. The instructions were sent out by email, but I'm sure that not everyone read my email super carefully, because that always happens. So let's see what questions you have.
Okay.
Step by step, how do we start? If you maybe bring up the training material, the lesson page.
So for example, if you go to lumi.csc.fi over here, and then once you're logged in, I hope everyone already made their account, because otherwise it will take a while. And then you just click on Jupyter for courses. And then you can make your own new reservation. So under the Quantum Autumn School, and this should be automatically here. And then, you can just quickly prepare a 2-hour. And, these are, I believe, just the default settings that everyone should come with. Yeah, there is the default settings versus the advanced settings. Yeah. This is still pretty much the default from there. Okay, it still seems to be from 3 hours ago, so not been updated yet. But if you go inside CAS 2024, inside content, and if you go to notebooks, hopefully you should see this one notebook called GHZ Estimator Attendees. So, yeah. Okay. So if everyone can see that, then that's great. Is this a notebook that you're running? Okay. And then probably some problem on my end. So for example, let's get started with importing the correct modules. And then there have been some issues with this, but hopefully we can set up Helmy. Okay. So just to break down what we did, now we are accessing Helmy through Lumi, and we have just imported the provider, and now the backend that will run on is Helmy. So you can already run the next cell, and you can see that our native operations are measures, identity, just the rotation, the phase rotation, and Control Z. We have 5 qubits, and this coupling map corresponds to what we had. And that's how Helmy ends up looking. So let's start with preparing the GHZ circuit then. So over here, you can see we have the Hadamard in the middle, and then control knots all the way across, and then we measure. And by default, we do initialize to the all 0 state. Now, if we convert to Helmy's native gate set, you can see that we now have rotation. When it's pi by 2, it's rotation. Yes?
Thank you.
Yes.
Why do you have a barrier before the last C0 gate?
Yes. So this will you will see the reality of running on a quantum computer, but essentially what I wanted to ensure was that qubit 5, all the gates that happen, like if you look over here, some of the gates are bunched at the start, and I do not want this to happen for qubit 5 because it appears to have a shorter lifetime, at least when I was testing this. So this is just some hardware-aware optimizations that I've already done. Yes.
Okay, thank you.
And yes, so you can see over here that we have phased RX gates, and then we have the virtual RZ gates. And then we can actually optimize this further because many of this, the RZ gates commute with the CZ gates. And before we measure, we do not need any RZ gates because it does not affect how the measurement works. So we can optimize that away. And you can see we essentially have the same circuit that I just showed you on the slides. Now, we can just go ahead and run this. So it will take about 10 seconds, but we do have many people running. So you may have to wait a bit in the queue. Yes. So once again, this is why I mentioned this is a prototype and it's currently uncalibrated. Because normally, as I mentioned, you would only see all zeros and all ones. But here, because qubit 5 is underperforming, we do have, it is flipping over here. So that leads to a pretty bad GHZ fidelity of about 33%. So we are not even at that 50% mark yet. But I'll wait for everyone to run this so you can get your own results so you can compare. But it should appear like this. If it appears better for you, congratulations. Until then, if there's any questions about the exact transpilation or anything you would like me to explain? So do we already have people with their own results coming in? And I assume it should, the results should look similar to this. Now, if you really dislike how this is looking, you can always just come to this cell and switch to the fake backend. And that will immediately give you better results. But this is an introduction to Helmy, not introduction to simulators. So we'll carry on with this. So now let's actually come back to the presentation. So now let's look at how we can optimize. So as I mentioned, this is a noisy quantum computer, but we can optimize away some of that noise. And that's the part which really helps us get, well, maybe not optimal results, but it always helps us get better results. So when we're trying to reduce errors, there are multiple levels and multiple ways of doing it. There's error suppression, which is very much on the hardware level. The lines are kind of blurry between them, but in general, you can say error suppression is probably out of your control unless you're doing like pulse level optimizations. When you're doing gate-based, then you come to error mitigation, which is what we'll actually be covering. But in the future term, we hope that error correction is the way that we get even better fidelities and actually manage to run large circuits, such as Shor's algorithm, for example. And I do believe my colleagues have some great talks coming out on the error correction part. But I'll just quickly mention that error correction, for example, through stabilizer codes or whatnot, it usually combines many qubits, and then you trade many noisy physical qubits for one very fault-tolerant qubit. Now, error correction can be described as a trade-off between the number of qubits you have and their quality. So you trade many bad qubits for one good qubit. Error mitigation requires us to run multiple circuits So we may need to do some extra circuits, we need to submit some extra jobs, but we can use the results from that to mitigate our errors. Okay.
Hi, question on the previous slide there. Do you have anything to say about the ratio between physical qubits and logical qubits? That ratio, was that always going to be the same, or what does it depend on? Are there good or bad logical qubits, or are they just always good by definition?
Oh, so the basic definition of a logical qubit is any, like, for example, I believe Quantinuum, or I don't remember the exact team, but they used 24 qubits to create one logical qubit. And that qubit had 10 to the power negative 5 fidelity. So that's about 100 times better. But that is, for example, still not good enough for Shor's algorithm or any of the long-term ones. And obviously, the definition of a good qubit really depends on your circuit that you end up running. But the good thing that you can do is that you can concatenate these codes somehow. So for example, if there's a 24:1 ratio and you're getting a 100-fold improvement, then if you, for each of those 24 qubits, if you had 24 more, then maybe you're getting 100,000. And it's recently been proven that because essentially you are adding more noisy qubits to a system, but this mathematical robustness outscales the added noise from these qubits. Now, obviously, you cannot just like use very bad qubits and expect to come up with something, but the general qubits that we already have on, let's say, IBM devices, 99.9% fidelity, 99.8% CZ or CX, which, you know, these are the benchmarks that everyone wants. Those are already enough to provide this improvement. But if you have a way better qubit, you need fewer of these. So it's really a game of mix and match. Okay, continuing onwards. So if you remember the labels, let's look as to how we can reduce the errors in each individual section. So we somehow, at least in superconducting qubits, we assume that our state is initialized to 0. That's the ground state. That's the most stable state. But there's ways to make this more robust. So one of the simplest ways is active reset. So for example, we just measure a qubit. If we see it's a 0, good, we leave it. If we see that it's a 1, then we apply an X gate and it's now at 0. There's also heralding, where instead of doing this apply, sorry, that got a bit loud. Yeah. So instead of applying this X gate, we just discard any circuits where our qubit was initialized incorrectly. But this comes with its own problems. So for example, if you have a 1% error on measurement, and then you have 10 qubits, then that 99% fidelity is already down to 90%. If you go up to 50 qubits, that's hovering somewhere around 55, 60%. I don't remember the exact numbers. And unfortunately, currently measurement errors are way higher than that. So heralding at least is, you would need too many shots. But I believe that the current NIST devices do not, not all of them are active, have the exact active qubit reset, because there are many technologies being developed. There's quantum circuit refrigerators developed in Alto. So those could be a way of quickly resetting our qubits. It's a field of active development, and hopefully you'll see this implemented more in quantum computers in the near future. Let's come to quantum gates, where there's a lot of errors happening there. So every gate that we run has an error attached to it. If you remember the error charts from before, even our single qubit gates had some noise, but more of the noise comes from our 2-qubit gates. Now, there are many, many error mitigation techniques. I would recommend just like scrolling through MITIC, for example, and you can see the ones that are already plug and play to implement, and they keep adding more every few months. So there's like poly twirling, where we can essentially replace a gate with an equivalent unitary, but we have a few added gates, and hopefully that cancels some of the errors out. Or at least one of my favorites, zero noise extrapolation, where we repeat a gate, and that should scale the noise up. And then if we do this multiple times, then, and okay, wait, I have slides for this, so I'll just leave it for that. So this is zero noise extrapolation is a noise mitigation technique where we vary the noise. So you can do this digitally, you can do this physically. You could just make your qubits worse, but you could repeat the gates. So each gate that you run is essentially going like once you can run your normal circuit, but the next time you could replace, for example, your 2-qubit gates with 3 copies. So over here, for example, you can see we have a C0 and a CZ gate where most of the errors are coming from. And then we can rerun the circuit with 3 times as many 2-qubit gates. And then we can rerun it with 5 times, and so on. And it should get, the results we get should be progressively worse. Now we can define an observable. So for example, maybe we know exactly what we are expecting. Let's say the probability of just getting a 0, or in this case, just the probability of getting a 1 after a single X gate. And there are many ways to fit this depending on the exact circuit that you have. So for example, over here, I only did X gates, an odd number, and I tried to extrapolate the errors away. So you can see after a while, the qubit just T1, T2 times, they come into play. But before that, we do have somewhat of a decent fit over here. And with this, we can estimate what the fidelity would be without the noise. And the way that we can extrapolate away this noise is quite useful, especially in large circuits. Now, coming to measurement, which if you saw that was pretty bad, readout mitigation is easily one of the best ways to quickly improve your results. So the simplest method we actually have is we prepare this confusion matrix. So for example, you prepare a 0 and you prepare a 0 like 1,000 times, and you get a 0 950 times, and you get a 1 50 times. Then you prepare, let's say, your ones, and you prepare 1 1,000 times, and then you measure, and then you see, okay, I'm getting the actual result, 1 900 times, 10% of the time it's causing an error. And so this creates a confusion matrix. And when we invert this and apply it on the actual results we get, then we can essentially remove this effect or try to mitigate the effect of these readout errors. So once again, I guess we can come back to the slides here. Okay. So yes, so this code was modified from NVIDIA, and I would really recommend reading through the literature. But since we have a lot of people and we don't want to use up, we don't want to use Helmi for the entire day today, we can just start preparing these 2 circuits. So the first circuit that we have, this will prepare all zeros. So we just prepare a circuit and then we measure it immediately. So now we can actually run it on Helmi, and we'll see the results in a bit. I'll try to get ahead of the curve, run some more jobs in the background, but yes. So over here, we prepared all zeros, and we can see that about 90% of the time, we do get all zeros. And if you actually look through it, for example, you'll see like, okay, 4% of the time, maybe qubit 1 has flipped. 3.5% of the time, qubit 2 has flipped. but it's very rare that two qubits flip together. Qubit 3 doesn't flip that much. Qubit 4 and 5, they're also stable, but two qubits flipping together is very rare, and you don't even see three qubits flipping over here. But on the other end, let's see how all ones react. And we will see that it will perform worse because T1 time exists, for example. So the one state is an excitation, and it is thermally at a higher energy level than the ground state, and it wants to dissipate that away, come down to the zero state. So we can see, oh, that's a lot worse than I expected, but we have about 50% success rate of preparing all ones. And you can see over here, for example, qubit 4 is really quite likely to flip, for example, or be measured unsuccessfully, qubit 3 as well. And now we can quickly just have a look as to how this looks. So this is, now we'll just prepare the individual confusion matrices because we ran all 5 qubits at once. So now we can see that we have the confusion matrices for each qubit. So you can see qubit 1, for example, it was about pretty symmetric, but qubit 4, it could only prepare 1 when it was supposed to prepare 1 about 75% of the time. And qubit 3 could only prepare it about 84% of the time. But you could see, for example, in all of these, when asked to prepare zeros, it could do that quite consistently. So let's just quickly look back at the actual values we got. So this was pretty much concentrated around all zeros, all ones, but there was the added feature of qubit 5 flipping, which means that we do have some peaks in the middle. Now, I'll explain the math behind this really quickly. But first, essentially, we have the confusion matrix per qubit. We can simply invert that. And then, essentially, by doing a tensor product on all of them, we are approximating the inverse confusion matrix for the whole system. Now, we can obviously do this in better ways, like instead of doing just 2 circuits per for the whole system, we could do 2 circuits per qubit. But that still leaves us with, that's still not, for example, the proper way. The proper way would be for us to prepare every possible state on a 5 qubit system, all 32 states, and see where that leads us. But oftentimes that's not really necessary. Now, because we are inverting a matrix and then we are applying that to the counts that we had previously, we could get some negative results. So when we do get that, we will try to correct for that by essentially finding the nearest distribution which has all positive results. And so after correction, we can see that our results are more concentrated along where they were already higher. Whereas they, for example, you can see over here, you only have these results in the unmitigated case. After mitigation, these just disappear. And so not a great improvement, like the result is still not above 50%, but we already have a much higher GHZ fidelity. And actually, let's come back to one of the other points that I had. So we started with making a GHZ state to estimate the GHZ fidelity. We saw that we got bad results. And then we saw that there are error mitigation techniques that we can use to potentially get better results. But one of the other things that we can do is just choose smarter algorithms. Is a GHZ circuit the only way to estimate the GHZ fidelity? Actually not. there's this one thing called multiple quantum coherences. So essentially, you can see that we prepare the GHZ state, and then we apply a phase to all the qubits. And then we undo our GHZ state. Actually, it looks like it's a bit wrong here. There should be a Hadamard here, but we'll come to that in a bit. And after we undo this, essentially we will apply, like the phase shift that we apply to, let's say, qubit 1 will be kicked back to qubit 3. And because we are applying, let's say, e to the power I5, but then it's applied 5 times, then over 2 pi, we will essentially end up getting 5 oscillations. So for n qubit GHZ circuit, we need to run this at least 2n plus 2 times for all these different angles, just basically subdividing over 2 pi. And the reason for this is, wait, it's a bit hard for me to see my own slides, just a second. Yes. So essentially, we can get a lower bound on the GHZ fidelity and then an upper bound. And for this, we essentially apply a Fourier transform. And so we can convert those frequency analyses into seeing how well the GHZ state would perform. Now, ideally, we only get all zeros and all zeros except qubit 3 being a 1. And then the ratio between these should be somehow sinusoidal. And I wouldn't bore you with the maths here, for example, but okay, I'd rather just have everyone run this right now. So we will run this on the simulator now. But hopefully we can explain this quickly. So first we define a parametrized circuit, and then you can find the original paper here. And then we define which angles we sweep over. Then we create all the parametrized circuits. And let's just have a look at how these end up looking. So quite interestingly, I guess you can see I already have some X gates here, which you would wonder why that matters, but we'll get to that really quick. But other than the X gates, it is similar to the circuit I just showed you. Now, once again, we perform transpilation. And then you can see that it's quite a short circuit, but we do have twice as many control NOT gates as we previously had. So for example, compared to the GHZ circuit, because this one is longer, it would benefit more from, let's say, zero noise extrapolation, because it's just a longer circuit. Now let's set up the fake backend. And let's just quickly run this. And you can see already that we got the results way quicker, because obviously this is a simulator. And now let's find the ratio between all zeros and the state where only qubit 3 is in 1, because we can ignore every other state as noise. So when we run this, the ideal case should be these 5 oscillations. And we can see that the red dots try to land on that. They do generally follow the shape. And if we calculate the lower bound and upper bound, we can see that it is about, for example, about 90%, for example. I will explain the math a bit more in a bit. But what I would really recommend is everyone actually explores this. So for example, if we go all the way up here, if you could just like comment out this line and rerun all those steps and compare what results you get. Alternatively, or I would recommend additionally, I would recommend coming here and changing the number of experiments you run. Change it to 30, 100, whatever, it should run locally for you and it should run in a second. And then you could compare how the actual values end up looking. So I'll give everyone like a few minutes to do that. And until then, do we have any other questions? You could try changing the number of experiments from this line over here. And you can try to comment out these X gates. And then just run all the cells again, and hopefully you should see some, and hopefully you can let me know if anything changes for the lower bound and the upper bound. Obviously, they will vary a bit because we are taking like only 16,000 shots.
Sorry, so here?
Yeah.
There is a question in the Zoom chat. I'm not sure if you already showed it. I might have missed it. So what do we change? Can you show it again?
Yes, yeah, that's highlighted here. Okay, so I hope everyone's run that already. And what you will find, for example, like I can do this really quickly as well, just to compare. Let's go 100. And yes, the results are still pretty good, and it's still about 90%. So even adding more or removing the X gates did nothing. But that's because, once again, we are running on a simulator. So I can now show you what it's like running on the actual hardware.
There you go.
So the reason for that X gate, for example, is because sometimes or not sometimes, you will observe a phase shift. So instead of lining up with the actual peaks, so these are actual results from Helmi when it was better calibrated, you can see that it's somehow off axis, and that obviously produces worse results. And it's not just a fluke, it's very stable. I reran this, and you can see that obviously this is the lower bound, upper bound, but you can see that both of them end up improving. And when I did these results, for example, this was still much higher than the GHz fidelity. So I had GHz fidelity about 60%, but even with the unoptimized MQC circuits, or sorry, not unoptimized, but without the X gates, with the phase shift, it was still better. The lower bound was still higher than the actual GHz results I had.
Can we
Yes.
make the bounds arbitrarily tight, or is there a limit to it? Like running more circuits
Yes.
improves or makes the bound tighter?
So mathematically, it shouldn't affect anything. What we are doing is we are just applying this Fourier transform, and we want our oscillations to be 5. But in reality, when you end up running it due to noise, you will, for example, have some more of a Fourier element of, let's say, just 1 or of 6. So when you end up running more circuits, it's somehow more concentrated along 5, or let's say the noise is more distributed. So the results appear to be better, but you are very much trading more circuits for better fidelity. Now, let's look at some other optimizations we could do. So each qubit has its own T1 time, and very quickly, if we just jump back to, for example, this circuit, you can see qubit 1 is running for the shortest amount of time, whereas qubit 2 has the longest gap between when it's first 0 and when it's 0 again. So we could change this order arbitrarily, but we could also choose it so that the T1, the qubit with the longest lifetime, has the longest wait time. And for example, anytime it's idling, for example, there's a T1 decay, but we can replace that T1 decay with, for example, X gates. So because the single qubit gate fidelity, while you have a single qubit gate running, you do not have this decay. Then obviously we could perform readout mitigation, zero noise extrapolation, any other method. we could increase the number of experiments we perform to achieve a higher fidelity. And when it's more noisy, then you can have some points that are off the axis. For example, over here, sometimes they just do not line up that well, like this point. But when you end up running it, it really matches up quite close. So if you average over, you can get rid of some of these distortions. So make our results less random. But essentially, what I'd like to get across is sometimes a smarter algorithm is better than all the optimizations you could choose. And error mitigation, obviously, there is an extra cost. So for example, the readout mitigation, we needed to run 2 extra jobs, and we got, well, I guess about 25% better results, which is a great improvement. But obviously, when you're running on a quantum computer, there's a physical cost, there's a time cost associated with that. So it's best to be smart about which algorithm you end up, or which optimization techniques you end up using. And the more hardware aware you make your problem. So for example, changing the way that each, like, okay, we'll do qubit 1 first and qubit 5 last. That, for example, may work well for Helmy, but if you end up running on a different device, then that all that optimization is just gone, because it's very hard to automatically do that. Okay, optimizing NISQ algorithm, it's still being actively studied, but there's this hope that many of these techniques can scale to larger NISQ devices. For example, I mentioned that heralding does not scale well with the number of qubits. But for example, readout mitigation, especially the simplest example I just showed you, that scales very well with the number of qubits. You can do it linearly, or you can even do it constant, just 2 experiments. And do we have actually any comments? Okay. Yep. And yes, that's it from my end. So thank you very much. And please let me know if you have any questions.
Thank you very much, Suhair.
Yeah.
Which questions do we have in the audience?
Thank you for a very nice presentation.
Thank you.
I have a question. When we changed the G8Z circuit to include RZ gates and then did the G8Z state preparation, but in the opposite direction, why did we do that? I didn't quite understand what this does.
So essentially, we are preparing a G8Z state, and then we are unpreparing this G8Z state, and we are applying this phase to each qubit. And if you are preparing the state correctly, and then undoing the state correctly, then all of this phase should come to the central qubit. And that's essentially what we are doing. So instead of the actual counts of all zeros and all ones, we are transferring the information into this phase. So it's just a different way of obtaining the same information, but it's more robust to noise.
Okay, so in the end, when we see this oscillation, we plot the phase of qubit 3. This is it?
Yeah, pretty much. This is like where does the qubit 3 end up lying on the block sphere? Because it should be somehow 0 plus e to the power I phi.
Yeah. Okay. Thank you.
Yeah.
So I also have a question.
Yes.
First of all, thanks for the great explanation. Very clear.
Yeah.
If you can bring back the slide
Yes.
with the new circuit.
This circuit?
Because you mentioned that the phase shift are done in hardware, right? Are done. So these RZs are actually not real gates. They are just calculated. And so if I understand correctly, then you just do the reverse of each one's with the phase kickback. But you're basically doing identities then? Like if you unite the 2 C notes for each qubits.
if you united the two C naughts, yes, but
Okay.
the RZ, well, the explanation that I believe we get for this is your block sphere is also rotating at a frequency similar to the block vector. And then there's the control electronics. And for example, if you have a phase shift in the control electronics, your block sphere is rotating and your block vector is as well. Your block vector keeps rotating and your block sphere just stops and then it restarts. And now suddenly, you end up with a Z gate. So it is somehow actually on the hardware as well. But we, for example, the traditional way of doing a Z gate or a RZ gate is we physically change the qubit frequency using, let's say, those tunable pulses. We can do this with Helmi, but we don't. With these tunable qubits, you physically change, and then you have to bring it back, and there's more noise associated with that. So instead of physically changing the qubit, we are doing this more on a pulse basis, I guess, or more on a software basis. But it is still actually done to the hardware.
Mhm.
Like you can measure it and see, yes.
Thanks.
Yeah.
Any other questions?
If not, then I guess I do have
There's one.
one quick thing to show. Oh, yeah.
Yeah, there's one question.
Yeah,
Yes.
I have a quick question.
Yeah.
Does the Lumi quantum computers does it support Qiskit primitives like estimator and sampler?
Yeah, so we are already on Qiskit 1.1, and I'll leave it to my colleague there. Yeah.
So we recently upgraded to Qiskit 1, but there's some things like the backend estimator V2 doesn't work, but IQM is working on that. So some of the primitives work, some don't, but we're currently exploring basically.
Yeah. Also, as just a last thing, I just ran while we were talking, I ran this on the actual hardware, and you can see that because of the same reasons that because of the qubit 5 and Helmi just underperforming, the lower bound and the upper bound are the lower bound is quite bad, but when this was running way better, you can see like the actual results we ended up getting. So oftentimes it's also the best thing that a NIST quantum computer can have is a good calibration. Because a few days after a good calibration, it gets worse and your results keep getting worse until you end up with a good calibration again. So obviously, the biggest tip I can give if you want better results is just ask the people, hey, can you calibrate this real quick for me? And that's it.
So Helmi has good days and bad days.
Yes, depends on when people are working.
It's a bit moody.
Yes.
Okay, so maybe that was the final question, final topic. Let's break up for, well, let's give Suhair another round of applause.
Okay, so welcome everybody to this session. We're gonna discuss about variational quantum algorithm, and in particular, we're gonna focus in about variational quantum eigensolver and the quantum alternating operator ansatz. There are gonna be multiple sessions about both of those, so I will this is gonna be repeated in time in the next days. But just to outline what is gonna be this 3-hour session. It's going to begin with some theory about projectors, operators, observables, and expectation values, just to clarify the mathematical framework that we're going to use to try to understand a little bit about the variational algorithm and the VQE theory. And then we're going to discuss, this is going to be just a theory session. So the hands-on session is going to be about the quantum alternating operator ansatz and the max K-cut problem. So for you that were in Gothenburg, the same, and the quantum school last year, there was a similar session with me and my supervisor friends that couldn't come today about the max cut problem. So this time we're going to just try to implement the max K cut problem. So the generalization to K colors. So this is where the hands-on session is going to begin, and this hands-on session is going to be about finding different encodings on a quantum computer when K is a power of 2, and when K is not a power of 2, we're going to discuss 2 different methods. So let's begin with a little bit of math. I hope everyone knows what is a projector operator, but a projector operator onto a subspace of the Hilbert space is an operator that acts on a quantum state and force all the components that are not in the subspace of the definition to be 0, and all the others to remain untouched. So this means that a projector operator is an operator that has the property that when squared is equal to itself. This can be understood in the sense that, like, if we project one time and then we reproject, all the components are already 0. So we expect it to be the same operator. So the idea is like, how can we describe in the bracket notation this operator on the Hilbert space? So let's suppose that we have a corner of the Hilbert space of dimension d. So it can be like written as a span of some orthonormal vector psi I. So these orthonormal vectors are quantum states such that the scalar product is equal to the delta function, so delta ij. So in this setting, a projector on this space can be written in the bracket notation as a sum from 1 to d of the singular projectors on these vectors psi I. So here, in this notation, ket psi, bra psi, this is an operator that projects along this vector here. So as we're going to see, like in the hands-on session, we're going to be using a lot of these operators. And in particular, we're going to be interested in implementing on a quantum computer the exponential of a projector operator. So this is the complex matrix exponential of a projector pi. And actually, we can see analytically how like this operator acts on a quantum state, because of course, expanding in a series, the exponential, we have that we can use the property of the projector, that's when the square is equal to itself, to rewrite this unitary here. This is a unitary operator, it's going to be a circuit, as a linear combination of the identity and the projector itself. This is just because, like, in this sum, all the terms are pi, except the first term, when pi to the power of 0 is identity. So the complex exponential of a projector will always have this form here. So let's take a look at, like, for example, the simplest case, where we want to, like, implement the projector of the exponential of the projector on the 0 state. So the projector on the 0 state is a matrix of 2 to the power of n times 2 to the power of n, where n is the number of qubits, that has 1 as first entry of the matrix and 0 other else, if we represent this matrix in the computational basis. So when we take the exponential, this matrix is going to be a diagonal matrix that has the phase e to the power of I theta in the position 0, 0, and 1 in all the others elements of the diagonal. If we ask ourselves how we can implement this operator on a quantum computer, this is exactly in the 3-qubit case how this operator will look like. And we can see that we just need to be able to implement a phase gate, where the phase gate is this operator here. There is a diagonal operator with 1 as first entry, and e to the power of I theta is the other one on the diagonal. And then use a multi-control of this phase gate and some X operators to kind of like try to understand why this is the form of the circuit related to this matrix here on the left. If we take, like, for example, X phase X, what is happening is just like we're just inverting the order of these two entries. So X phase X is e to the power I theta 1. And what we want is actually this operator here. So we want to apply this phase here when all the other qubits are in the 0 state. So I hope that this is like clear in some way, but we're gonna like repeat it multiple times along this this journey. There are questions, or I can move on. I will move on. Then let's discuss about observables, because what we want to do in this theory and this session is try to solve combinatorial optimization problems. So the idea will be to try to encode the cost function of an optimization problem into an observable that we can measure on a quantum computer. So let's just discuss a little bit about what is an observable. An observable H is a self-adjoint operator of the Hilbert space. So this means that through the spectral theorem, we know that all the self-adjoint operators admit an orthonormal basis that diagonalize this operator, and in this basis, all the eigenvalues are real. So this means that we can rewrite this observable H that will encode our combinatorial optimization problem into a sum of eigenvalue real lambda I times projector on the state psi I. So in the specific case of the projector operators itself, this was the form sum over I psi I. So the projector operators are self-adjoint operators with a spectra that is composed only by 1 and zeros. While in general, we will have like generic eigenvalues. In physics, for example, these H observables are called Hamiltonians. The eigenvalues are called energies, and the eigenstates are usually called energy eigenstates. So what we're gonna see is that what we're interested in this with this quantum algorithm is to like try to obtain on a quantum computer an algorithmic way to obtain the ground state. So the ground state is the energy eigenstate related to the lowest energy. So what we're gonna be, what we're trying to do is like encode a combinatorial optimization problem into an observable H, and the optimal solution, so the minimal solution, gonna be related to the ground state of our observable H. But to once we have encoded a problem into some observables, what we want to do is like to measure this observable on a quantum computer. So we have to discuss about what are the expectation values for a certain observable. So let's suppose that we have a quantum computer, a gate-based quantum computer as the LUMI one, for example, and we can prepare using a quantum circuit that apply the unitary U, a certain quantum state phi. And we ask ourselves, if we prepare this state phi and we want to measure the observable H, what is the expectation value? What is the output that I'm going to obtain from this circuit that prepared phi? So the expectation value formula is expressed in equation 3 here. And we can see that like the expectation value of H preparing phi is the sandwich of H between phi and phi. Or using the fact that phi is U applied to 0, is the sandwich between 0 and 0 of U H U dagger. But this does like it's not like intuitively clear what is this expectation value written in this form. So it will be a little bit clearer if we employ the spectral theorem. So we know that the observable H is self-adjoint. So we can write this term here, substituting H as sum over I, lambda I, projector on psi I. And what it remains is what it's stated in equation 4, that the expectation value is the sum over I of the eigenvalue of the energy lambda I times modulo square the projection of the state that we prepare on a quantum computer respect to the eigenstate psi I. So just the weighted sum of like eigenvalues time projection along that eigenvector. So that means that if we prepare on a quantum computer an eigenstate of the observable H, we will measure exactly that energy. Or if we prepare exactly the ground state, we will measure the lowest energy. And that's going to be the goal for later. The goal to achieve this is going to be through a variational algorithm. So we're going to use some variational methods to try to prepare this state, some state on a quantum computer. So the variational methods are all based on the fact that the expectation value for all the possible states that we can prepare on a quantum computer are lower bounded by the energy of the ground state. So this means that whatever observable we choose and whatever state we prepare, the expectation value is going to be always at least greater than the lowest energy that we can measure. And this is like kind of clear when we take the formula from before of the expectation value and just we lower bound each term of the sum, substituting lambda I with lambda min. So this is clearly like a lower bound here. We're like this less than equal. And then what happens is in this sum, we can take lambda min out of the sum, and what it remains is just a sum over I of all the amplitude square of a state phi on an orthonormal basis that is complete. So this sum here is equal to 1, and what it remains is the lower bound that we were, like I was saying before, the fact that the expectation value is always lower bounded by the ground state energy. So the idea for this variational algorithm is to try to encode the problem that we want to solve on an Hamiltonian, and in some way prepare some parameterized state. So some like quantum state that could be on a classical computer, maybe a vector or whatever. But the idea is like to try to optimize, to minimize, sorry, the expectation value respect to the parameters of this wave function to get as close as possible to the ground state. So looking at the right part of the slide, to get a little bit more like an intuition of what happens, let's suppose the gray area is the Hilbert space, and the solution to the problem, so the ground state, is the red dot. What we do is like we choose a parameterization for a subset of the Hilbert space, because exploring the whole Hilbert space is too big. So the idea is like we want to like explore a smaller space, so we choose a parameterization for some like subset of the Hilbert space, and we begin with some parameters θ0. And what we do is just like measuring each time the observable h that we want to solve, trying to minimize this expectation value and move from the yellow dot to the green to the red dot. And this is what it's all about, the variational quantum eigensolver. The variational quantum eigensolver is just like a variational method where the preparation of the trial quantum state is made through a quantum circuit, so a parameterized quantum circuit. So again, we have that the energy of the lowest energy is a lower bound for the expectation value, whatever state we're gonna prepare on a quantum computer through a quantum circuit. And what we have to do to have this variational quantum eigensolver is, first of all, try to like rewrite the Hamiltonian in terms of Pauli strings. So we're gonna take our problem Hamiltonian and decompose it in the set of Pauli string. Where a Pauli string, I assume all of you know what it is, but it's just like for n qubit is the tensor product of the Pauli operators and the identity. And once we have this encoding, we're gonna have like the Hamiltonian will look like a sum of weighted Pauli strings. And what we have to choose next is what is called the ansatz. So the way the quantum circuit, the parametric quantum circuit, that will represent our set of states that we can explore. And so once we have chosen this ansatz, this is going to be like a really important part of this variational quantum eigensolver. What we're going to do, like step by step, is minimize the expectation value of the energy. So minimize the parameter of the circuit of the expectation value of the sum of the singular measurement of the Pauli strings. So if we look at the picture here, this is like kind of like have everything that we need. So what we do is we begin our algorithm with like on the 0 state of the quantum computer, and then we define a certain ansatz. This ansatz is a quantum circuit with some parameters. Here, for example, it begins with 2 CNOT gates that are like parameter free, and then we have a layer of rotation along the z-axis and the x-axis. And these parameters here are free. So what happens here is that at the end of this blue box, we will have a parametric quantum state. So we begin our algorithm with some initial guess, some initial parameters θ0, and we input this parameter in the circuit. So then we have an initial state phi0, and through the basis change, we will measure Pauli string by Pauli string, or even multiple Pauli string at the same time. We will measure here at the end the expectation value of the observable h. Then what we do is just like this is going to be a scalar value, so we input this scalar value into a classical optimizer, and this classical optimizer is going to output a certain set of new parameters theta that we're going to input again in our ansatz. So this create a loop, like what is called quantum classical loop, where we just prepare quantum states, measure observables, input the expectation value on the optimizer, and keep going in this way until in some way we converge somewhere. This is what is called a hybrid quantum algorithm. Is hybrid because we have a quantum part where we prepare state and measure observables, and a classical part where we just optimize the parameter of the problem. The problem of this like variational quantum eigensolver is that heuristic algorithm. So there is like no probable guarantee about the runtime, for example, and the performances even. So it could be that like this problem has multiple minima and maxima, and we're gonna get stuck in some minima and maxima. But in any case, this is what it is. So to like execute a variational quantum eigensolver, we will have to do two main choices. One choice is how we describe the parametric quantum state. So it's the ansatz choice. What is the circuit, the parametric circuit that we want to use to minimize the expectation value of H? So this is like a critical part of the variational quantum eigensolver, and there is a lot of literature here about what to use, when it works, when it doesn't work. But three are the main characteristic that we should like try to take in consideration when designing an ansatz for a variational quantum eigensolver. The first one is the expressibility. So we want that the range of feasible state that we can achieve is big enough to describe the ground state. So in some way it is related to the green area. We want an ansatz that the green area at least is close enough to the red point. If not, we will never get there. The second thing that we need to require is the trainability. So this refers to... So the second like characteristic that we should require from the ansatz is the trainability. So the ansatz must be like trainable in the sense that we should like being able to like optimize this set of parameters in a finite amount of time. So actually what happens is that like the expressibility and the trainability are two characteristics of the ansatz that are closely related and usually inversion like related, in the sense that like ansatz that are too expressible usually are really hard to train, in the sense that what is going to happen that is that the training space is going to be really flat. But there are many like multiple problems. Another characteristic that we should take in consideration, even in the actual era, the NISQ era, is the depth of the circuit. So our ansatz, when run on a real quantum hardware, gonna suffer from noise. So we can maybe have like a really expressible circuit that use a lot of parameters and whatever, but if the circuit is too long, it's gonna be too noisy. So these are kind of the three main issues we will have to face choosing a proper ansatz. So here I just provide you two examples of different ansatz that could be used on a quantum computer. The first one on the left is called the hardware efficient ansatz, and it's called hardware efficient. Why? because we have that is composed by rotations and CNOTs, and the hardware efficient part is just the fact that we choose the CNOT to just match the architecture of the device. So the circuit, like for example, in a 3-qubit case, looks like in the picture here, where we have some rotation along the x and the y axis with some free parameter, and then some entangling gates. So this, for example, will work really well on a linear architecture. If we, for example, was a linear quantum device and we want to use this CNOT here, we will have to use some swaps and stuff, so it's not going to be efficient. The problem of this ansatz is like it's really generic. It's even too generic. In fact, it's not related in any way to the problem that we want to solve, but can work for some things. The other example that I want to discuss with you is the Hamiltonian variational ansatz. This is an ansatz that is more like related to the problem that we want to solve. So let's suppose that like we have that the Hamiltonian H could be like written as a sum of Hamiltonians, Hj, and they will not necessarily have to commute. We just prepare as a parametric quantum state. One layer will be just like the exponential with a free parameter or of each of the terms of the sum. So let's suppose that like H could be written as H0 plus H1. So the Hamiltonian can be written with two terms. For example, one term in the Z basis, one term in the X basis. What we do is just like the ansatz will look like this. We begin with a certain initial state phi 0, and then we alternate the power of the complex exponential of H1 with a free parameter, and then the complex exponential of H0. In this case, because we have only two terms. If we have multiple terms, we're going to have a sequential exponential of all the terms in the Hamiltonian. So these are more like problem-related ansatz, because we are using as gates kind of like the terms of the Hamiltonian. So this ansatz seems to work for some, like, for example, physics problem or chemistry problems. But here we're going to have to deal with the optimization, combinatorial optimization problems. So let's just move on. In case, if you have some questions, maybe this is a good moment to ask questions. If not, I move on. So the other choice that we have to make. Yep.
You say something about the expressibility of the hardware efficient ansatz for one layer. Can you sort of, what is your state space that you can reach? I guess you can't reach all possible states with just the one layer of the hardware.
With one layer, no. In fact, like the thing is, like, here we have like it's a 3-qubit system, so we have like 8 computational basis states, and we begin, for example, from the 0 state. So what we have to kind of express is like with only one layer, we can't reach any state. So here we get just like the only type of entangle that we have is the linear entangle. To like maybe entangle in different ways, you will have to use multiple layers of this stuff of this type. In some way, like the expressibility can be quantified. So it's like there is a way that, like, in literature is like how far you are from the R measure. So like from the equal distribution of all the unitaries. So in some way, how far you are from being able to prepare all the states. And one layer is not a problem. It's like it's not expressive enough. But if you use multiple layers, it's really easy to get this expressibility really quick. So if you use like multiple layers, then depends on, of course, on the number of qubits. So more qubits you use, the more layers of this type you will have to use. But it's a really expressible like ansatz that maybe sounds like something good, but actually is not so much. To be too much expressible is not usually a good idea to run these algorithms.
Yeah, but theoretically, would the state space grow exponentially with the number of layers you have here?
Yeah, yeah. So then that's what I mean. It's like you don't need so many layers to like achieve this expressibility of the whole Hilbert space, but one layer is not enough.
Yeah.
Well, for example, here is a kind of different. For the Hamiltonian variational ansatz, it's harder to describe this. But yeah, so the other choice that we have to make to run a variational quantum Hegel solver is the choice of the classical optimizer. So the loop was we will have to deal like which optimizer we want to use to solve the problem. And there are 3 main categories of optimizers that we can use. And here, like, there is a lot of literature that comes from, for example, machine learning and so on. But the 3 main categories are like the gradient descent base. So these are like optimizer that like rely on the ability of analytically obtain the value of the gradient at each point of the variational quantum eigensolver to then like just like optimize the parameter in the direction of the gradient. And two examples are, for example, the gradient descent that is used in classical like optimization. And then there is like the quantum natural gradient that is kind of like a quantum version of the gradient descent. The second category is just the stochastic gradient base. So these like don't rely on the ability of calculating exactly the gradient, but on the ability of approximating the gradient with some sampling. So we random sample the gradient and then like optimize at each iteration. And examples of these are, for example, the SPSA or his quantum natural partner, QN SPSA, or for example, they're really using machine learning, the Adam optimizer. The third category is the gradient base, the gradient free. The gradient free are the one like some optimization optimizer that don't rely on the gradient, but on some other like tricks on the parameter space to converge to the minima. So there are these 3, and in our like in our end-sum session, we're gonna use the Cobila The decobila is like a gradient-free optimizer that use some tricks to like look for the minima. So let's discuss about the case of the quantum alternating operator ansatz, the QAOA, what is called QAOA. This is a specific type of ansatz. So this is like our choice for the ansatz is this quantum alternating operator ansatz that is specifically designed for combinatorial optimization problems. So let's begin by introducing a little bit of how to define a combinatorial optimization problem for a binary problem. We have an objective function f. So f is a function from the set of bit strings of n bit strings, so with 0 and 1 for n bits, to the real scalar values in R. And what we want to do in a combinatorial optimization problem is just to looking for the optimal vector x star that minimize this objective function f. So we are looking for the binary bit string that minimize or maximize, depend of course on the problem, this objective function f. But of course, like dealing with this problem, some of this problem could be like easy to solve on a classical computer. Some other are NP hard, and there are multiple ways of trying to solve this problem classically with maybe heuristic or some other strategy. But here we want to deal with trying to solve this problem on a quantum computer. So what we have to do is try to encode a combinatorial optimization problem into a gate-based quantum computer. So the first thing that we have to do is like encode each binary string into a quantum state. So this is like, let's suppose that we take a binary string here, and we map each binary string to the computational basis state that represent that binary string. So for example, we have 2 qubits, the 0, 0 string will be the 0, 0 state of a quantum computer. So first qubit in the 0 state, second qubit in the 0 state. So the encoding is actually, it's not hard, it's straightforward in this case. What we have to do later is to encode the objective function that we want to optimize, so to minimize or maximize, into what is called problem Hamiltonian. So to an observable H, such that if we apply H to a computational basis state that represent a binary string, the expectation value will be exactly the objective function related to that binary string. So this means that Z, computational basis states, are eigenvectors of the observable H, and the eigenvalues are exactly the objective function. So this means that this problem Hamiltonian is a diagonal operator of the Hilbert space that has this property here. And what we want to do is just like look for the ground state, because the ground state is the binary, the computational basis state that has the minimal eigenvalue fz that will correspond to the minima of the objective function that we want to solve. So this is really important. Like in this case, we have that for combinatorial optimization problem, the eigenvectors are all the computational basis state. This is something that, for example, in VQE is not true. When you have like quantum chemistry problem, the eigenstates are not the computational basis states. So here, like we have this characteristic for the combinatorial optimization problems. Okay, so how we do this? We have to design like to find a proper ansatz. So this proper ansatz for like combinatorial optimization problem is called quantum alternating operator ansatz, because it's composed in this way. It's a quantum state that depends on 2 vector parameters, gamma and beta. And we start with an initial state phi 0 that usually is taken to be the equal superposition of all the possible binary strings. So all the possible computational basis states. So this phi 0, if we look at the circuit, can be prepared. We begin with a 0 state and we apply the Hadamard gate on each of the qubits. So here, after these Hadamard gates, we have the initial state phi 0 is the equal superposition of all the computational basis states. And then we alternate 2 operators. One operator is the phase operator, UP, that depends on gamma. And the other operator is, UM, that depends on beta. The UP operator is called phase operator or problem operator, and the other one is called mixer operator. So the UP, so the phase operator, is taken to be the exponential, the complex exponential of the problem Hamiltonian. So it's, as we said, the problem Hamiltonian is a diagonal operator on the computational basis. So the exponential of this operator is a set of phases with an amplitude that depends on the specific binary state. So this is a diagonal operator too. This is something that we will have to remember. While the mixer operator usually is taken to be the rotation gates around the x-axis with the parameter beta for each qubit. So if we look at the picture here, we see like this is a two-layer case where we begin with the initial state that is the equal superposition of all the possible state, and then we apply the problem Hamiltonian with the parameter gamma 1. The circuit is not shown because depend specifically on the combinatorial optimization problem. And then the second operator is the rotation for each qubit with the same parameter beta along the x-axis. So what happens is just like, this is a two-layer case, so we alternate these two times, and then we measure on the Z basis to obtain the expectation value at each iteration of the observable HP. So this is like the whole ansatz explained for the quantum alterning operator. And this is, for example, what I will ask you to plot in the hands-on session, where we have on the left part what is called the energy landscape. So when P is equal 1, yes? Yes? The index here? Yeah, here I mean that like I apply for each qubit a rotation along the x-axis. So it's a product if I define Rxi as the operator that apply identity on all the other qubits and Rx on qubit I. So this is correspond to Rx exactly. Yeah, it was like not clear. Thank you. Okay. So if these are other questions, I can stop and not go. So yeah, in the exercises that I would like you to like plot these two examples of plots. On the left part, we have what is called the energy landscape. So the energy landscape is like the plot of the energy respect to the parameters gamma and beta, gamma on the x-axis and beta on the y-axis of the expectation value on the layer p equal 1. So when we have only one layer, we have only two parameters. So we can just visualize how the landscape look like. And here, for example, this is for a max-cut problem, where we have that in the region between pi over 2 and pi over 2, this problem is almost convex because we have like only one minima and one maxima. And so like it's gonna be easy for our optimizer to get here. That is the minima of the landscape. But this energy landscape in some way tell us even something about the problem, how hard it's gonna be to solve this problem. Because it will maybe have like multiple maxima and minima and stuff like this. So, but this is not the case. On the right part is another plot that I would like you to do is like the performance respect to the depth, so respect to the number of layers of the algorithm. So here on the y-axis we have this approximation ratio that is like this parameter that like tell us how good is the output solution. From 0, that is the worst solution to the problem, to 1, that is the best solution to the problem. So here we can see, for example, that for the problem with this landscape of p equal 1, we begin already with a kind of good solution, but with putting more layers and optimizing properly, we can converge to the right, to the optimal solution of the problem. And here I just show you the case where like all the optimizers work, but the nether mid, in this case, with a finite number of shots, doesn't seem to work. Okay, so yeah, from now on, this is gonna be the theory about the max k-cut problem. That is the problem that we will try to solve in the hands-on session. So for those of you that were here last year, we discussed about the max cut problem. The max cut problem, this is like the generalization to the K case. So the max K cut problem is a graph problem. So as the one on the right part of the slide, well, for example, here we have five vertices, 8 edges. And this is an example of a max tree cut problem. So we have 3 colors. So we have to partition this graph in 3 different partitions in such a way that we maximize what is called the cost function. This cut function, sorry. This is called the cut function, and we were looking for the max in the case of K colors of the cut function. This cut function is written like this. It's just like the sum over all the edges of the weight of the edge times 1 if the color of the vertices attached to that edge are different, and 0 otherwise. So let's suppose that all the weights are positive, and let's look at this graph. Here, if we take this edge here, this edge has 2 different colors on the vertex, blue and violet. And so this edge will contribute to the sum because they have different colors in different positions in the 2 vertices. If we put, for example, this is like actually the optimal cut. So this is the max cut of the problem because each of the edges of the problem are cut. Each of the edge has 2 different vertices at the end. But if we, for example, instead of this, we take here the blue color, what happens is this is not going to be the optimal cut. Why? Because we have blue, blue, and so this edge and this edge will not contribute to the sum. So this kind of problem is what we would like to try to solve on a quantum computer, because even classically it's known to be NP-hard. Already even the max cut problem, where we have like only 2 colors, this problem is already known to be NP-hard. So classically there are a lot of like different strategies to try to solve this problem. Some like attacks are heuristics, so are heuristic algorithms that are not like they run there's no guarantee that run in a polynomial time and no guarantee about the performance, but it seems to work really well for some specific graphs, for example. But the other kind of attack classically is the approximate algorithms. So approximate algorithms are efficient algorithms, so like they run in a polynomial time, and they provide some probable guarantees. So this means that we know that the solution in output from this approximate algorithm are at least good as. And this like how to quantify how good is a solution is usually done through the approximation ratio that is defined in equation 8, where we have the approximation ratio is the the fraction between the output from the problem, from the algorithm, sorry, minus the worst solution divided by the optimal solution minus the worst one. So it's just like a ratio between how good is your solution respect to the best one. So, for example, in literature, it's really famous, the max cut case, where like in the 95, Gosman Williamson came out with like an approximation algorithm that can approximate the max cut problem, so this NP-hard problem, with an approximation ratio of 0.878, so actually not so bad, in a polynomial time. So this algorithm will run in a polynomial time and give you a solution at least as good as this. And what happened then in time is like, I think in 97, like someone else come and generalize this algorithm to multiple colors, so to multiple Ks. And this is like the approximation ratio that is guaranteed by this algorithm. Okay, so this is like kind of like the introduction to the problem. Now we will have to deal with try to encode this problem on a quantum computer. So I check a little bit how it's going with the time. Okay, so first of all, we have to encode the problem on a quantum computer. So for each vertex, we have that we will need a certain number of qubits because we will have k colors. So let's suppose that we have k colors. We will need at least CIL of log 2k qubits, in the sense like If we have the max cut problem, we have two colors. So the first color is going to be represented by the 0 state, and the second color is going to be represented by the 1 state. If we have three colors, sorry, then we will have to encode these 3 colors on 2 qubit at least, because we want to map this on a qubit system. So for example, it could be that like the first color is 0, 0, the second color is 0, 1, and the third color is 1, 0. This is a possible encoding that we can do. But this is the fact. So to encode a whole graph problem, a whole max k-cut problem on a quantum computer, we will need V, where V is the number of vertices, time LK qubits. Okay, but then the encoding of the vertices, it's okay. So then what we need? We need to like represent the cost function, the cut function as a Hamiltonian operator. So this means that like the idea is like to write the problem Hamiltonian as a sum of terms that depend on the edge, with sum over the edges, the weight of the edge time a Hamiltonian HE. This Hamiltonian HE must kind of do exactly this. Must be 1 if the colors are different and 0 otherwise. So this kind of like look like as a projector operator, who is like this operator that like is 1 on certain computational basis state and 0 on the others. It's going to be a projector operator. So the idea is going to be to, instead of write HE, we're going to write it as identity minus H hat, where H hat is an operator that is 1 if the colors are the same and 0 otherwise. So we just like rewrite in this way because it's going to be easier to implement on a quantum computer. And once that we find this specific H hat, the circuit, the phase circuit is going to be just the exponential of this operator. So H by H, like edge by edge, sorry, we can write this operator as a product of terms for the single edge as a global phase that we will not care so much about, times the exponential with gamma times the weight of that edge of H hat. So all what we will have to do is try to understand how H hat look like. Who is this operator and how we can implement this operator on a quantum computer. So I hope until now it's kind of clear the problem. If not, I would like to be like more exhaustive because it's going to be the exercise about this. So the thing is this H hat operator is then what I was saying, a projector operator, because what we will have to do is like we're looking for the binary strings such that if this is a projector, is the sum on projector on the state I, tensor projector on the state J, when I and J represent the same color. So this operator here, that can be written like this, is if we have two registers, one register for the vertex A and one register for the vertex B, when we apply H hat, this is a projector on 1 if I and J represent the same color. So to make it a little bit easier, maybe I start with the max k-cut. The max k-cut is easy. The max k-cut problem, we have two colors, and for each edge, we are looking for the operator that has this form here. First, we have a sum of two projectors. Two projectors where like the first term is like the first qubit is on 0 and the second one too. So we have both qubits are in the 0 state. And the other option is that both qubits are on the 1 state. So this is like represent both the case of when both vertices has the same color. So this is a diagonal operator and is a projector operator that projects or in 0, 0 or in 1, 1. We're gonna just like generalize this to multiple colors. So, well, in general, the fact is like this operator here is identity minus ZZ, where ZZ are the Pauli operators, and the max-cut Hamiltonian can be rewritten in this form here. So sum over the weights of this hedge here operator, so 1 minus zi zj over 2. And if we look at how this operator look like when exponentiated, is a diagonal operator with some faces that depends, is like minus when are the same color plus when are different colors. So this is like 0, 1, 1, 0, different colors on the edges. And
So
this is...
Can I interrupt with a question from HackMD here? So I'm not sure when it was written down. It could have been 5 minutes ago. Seems like you have, as you add colors, the approximation will get better. Is there a reason for it?
Yeah, actually, well, yeah, the reason is actually pretty intuitive in the sense like the more colors you have, the more possibilities you have to like take decisions for each edge. In the sense like if we take this problem here and we make it a max 2 cut problem, then we will not be able to cut each edge. So the more colors you have, the more you can choose for each vertex a different color, and then it's easier to cut all the edges. And in fact, like let's suppose that we take this problem here and we said that we do the 4 cut. To solve the 4 cut, you need just 3 colors. So the 4 cut is easier respect to the 3 cut. And in fact, this is what we see here, for example. But it's like the reason is not so simple, of course, but it's kind of related to the fact that the more color you have, the more it's easier to make good choices for the approximation algorithm. I hope it's clear, but yeah, this is kind of the reason. There are other questions?
There is another question from the shared document about where one can find the literature about the solution for the approximate algorithms. But this is something that can be filled in later, maybe.
Yeah, I can. I mean, it's like Gozman-Williamson is the algorithm, and there are a lot of like literature related to that. Wikipedia page for MaxCut is way more than enough, but like I can.
Wikipedia page for MaxCut.
They will discuss about this algorithm. But yeah, this is the max k-cut. So we get exactly what this operator h hat is. It's just like a projector operator that project on states that represent when like the first register represent the same color as the second one. So let's look, for example, at the case when k is a power of 2. So when k is a power of 2, we can like kind of straightforwardly map each color into one and only one computational basis state. So let's suppose the case of like the max 4 cut problem. We have 4 colors. 0, 0 is going to represent the first color, 0, 1 the second one, 1, 0 the third one, and 1, 1 the last one. So for each color, there is only one computational basis state that represent that color. So in this case, this is the encoding. Ci, the color, the ith color goes to the binary representation of I. And the Hamiltonian h hat has this form here, where we have the sum from 0 to k minus 1 of projector on I, tensor projector on I. So this is exactly the form that we are talking about. I. This is, if we look at the MaxCut, is 0, 0, 1, 1. So these are projector operator that projects on k states, because the sum goes from 0 to k minus 1. And we need to be able to implement the exponential of this HE hat. And this can be done using a set of C naughts from the register A to the register B, and the projector operator on the register B 0, 0, on the 0 state. Let's try to understand why this. Okay, so the C naught operator from A to B correspond to the like this part of the circuit in the figure, where we have that we entangle the register A to the register B bit by bit. So like first qubit of the register A entangle first qubit of the register B, second qubit of the register A entangle the second qubit of the register B, and so on. So this is the circuit that represents CX A to B. When we apply this operator here to our computational basis, two computational basis states, one in the register A and one in the register B, what happens is the register A controls the register B. So the resulting state is going to be, again, the same state for A, but for each qubit of the register B, we're going to sum modulo 2, the entry of the register A. So let's suppose that we have one qubit, so the max 2 cut. In this case, we have this sum could be, we could have 0, 0. If we have 0, 0, what happens? The C0 don't activate, so we have that the register A is going to remain in 0 and the register B is going to be 0. If we have, for example, 0, 1, we will have to sum the register A is going to remain in 0, but the register B is going to be 1 plus 0, 1. So it's going to remain in 0, 1. So what happens with this kind of like C0 gates is that we're just summing the bit of A to the bit, the bit of A to the bit of B. So what happens is that if the two bits are the same, this state is 0. If the two bits are different, this state is going to be 1. And this is really important because if we apply this operator here to a computational basis state, if QA and QB are the same, so the binary string of A is the same as the binary string of B, after this operator, the register B is going to be in the 0 state, because that means that bit by bit, we were having the same representation. So this is like the trick. We use this CX A to B to have a state that is, if the second register is in 0, that means that two registers were like representing the same binary string. And then, after this, we apply the identity tensor, the projector on 0. So this operator here is going to be 1 if the second register is in 0, and 0 otherwise. So that means that like using these two operators here, I'm going to have, I get this, my connection is unstable. I don't know. That's not good. If there is no problem. So what happens is like if we combine this operator and the projector, the resulting operator is exactly the H hat. So I don't know if like here stop me if you didn't explain properly myself here, because it makes sense. There are a lot of math in some way, but the idea is just like this circuit here. When acts on a computational basis state, we will have that the second register going to be in 0 if and only if the initial, the two registers were already in the same binary string. So after applying this, the identity on the first register and the projector on 0 on the second one, we get exactly what we were looking for. But the thing is, like, we want to implement the exponential of H hat E. So this is just a basis change, so we can like take it out. And in implementing the exponential of this gate here correspond to taking this circuit where we have C naughts, exponential of the 0, 0, C naught back. So this is like the exponential that we have seen in the first slide. And this is the whole circuit for two vertices I and J of our problem. So now what I would like you to do is like to try to implement on the Jupyter notebook related to this session, the edge for a max 4-cut problem. So I want you to implement this edge, the circuit for this specific 4-cut problem edge, and then try to plot the landscape and the performance for different depth. So to do so, I assume I should show you where is the notebook, and the notebooks must be in I can see from here. Why? Okay. The notebook. Why it's so slow? Okay. So if you go to lecture material, and then go to tutorial variational quantum algorithm. It goes directly to the this page, and you go to the GitHub repository and just download this this notebook. And once you download it, you can open it on your, for example, my Visual Studio Code, and we will have this this notebook. So I wait a little bit until you try to have it. But if you have questions, let me know, so we can even try to clarify. Yeah, I show again. If you go to the lectures part, I don't know if you know how to get here. I hate that fact that I have. If you go to the lesson material in ACMD, that is the page with the if not, it should be in the mail like a link. But... Got it? Okay, then to lesson, you go to tutorial variational quantum algorithm, day 1. Then you open a notebook that you want to download. So just add it on GitHub.
The notebook will be on Helmi, though, in the course environment.
Okay.
I believe. Modupe, yes. So this is already I mean, cloned and updated on there. But this is if you're running locally on your local classical computer, then you should clone this repository or download it.
Okay. Yeah, I'm gonna run it locally.
Okay.
Because
so if you click code and just to show it, I mean, in the top left corner.
In the left corner.
I mean, just like the main page of the repository, left.
Yes.
Yeah, basically. And then just the green button, how to clone. Something like that.
Yeah, then you just clone. Let's make another.
If you don't have Git installed locally, one can download a zip file.
Yeah. So if everyone has the notebook, I can begin like describing a little bit how it works. So I go. Thumbs up. So the thing is, like, we begin defining a little bit the problem. So the problem is we want to solve with the max 4 cut, and we will try to do this using the QAOA package and the network X package. So if you don't have it, install it through pip install, and so just pip install QAOA and pip install network X. And once both are installed, just like it's needed to we have to define a graph problem class from the QAOA.problems. So we import QAOA.problems graph problem. And in this graph problem, we will have to input a network X graph that will represent our problem and the number of vertex per qubit and the number of qubits per vertex. So let's have a look at the first class. The class is going to be this max 4 cut class that takes the graph problem, and the number of qubits per node is going to be 2 because we are dealing with a max 4 cut problem. So we have 4 colors, 2 qubits. In fact, here we declare color by color who they are. So color 1 is going to be 0, 0, color 2 is going to be 0, 1, color 3, 1, 0, and color 4, 1, 1. And what I want you here to do is just to define on the module create edge circuit, the circuit related for one edge. So using, in this case, you will have to use the CNOT gate, the control phase, and some X operator. I want you to implement this circuit on Qiskit representing the edge. So just to be back, is related to this structure here. So once you have implemented this circuit, we can kind of like define the circuit for the QAOA. So I give you some time for trying to implement this circuit on Qiskit. So it's gonna be this. So if everyone is okay, I maybe move on and show you a little bit my solution. There is already a file that is already compiled. But, okay, so what we have to implement is the circuit from before in the case of two qubits per vertex. So we will have to apply the C0 operator, Cx, on Qiskit from qubit 0 to qubit 2, because we have to entangle the first register to the second register bit by bit. So it's going to be Cx from 0 to 2, Cx from 1 to 3, and this is going to be the part of the circuit related to the Cx from A to B. Well, this is going to be the part of the circuit related to the exponential of the 0, operator, the 0, projector. And to do so, what we have to do is like apply the x on qubits 2 and 3, because we have to apply only to the second register that is composed by qubit 2 and 3. But we have to implement the control. So to do so, we use the phase gate. So the phase gate takes in input a parameter theta and a control of 1 qubit, because in this case, our register is composed only by 2 qubits. So we have to implement a control phase operator. So then what we have to do is to append the phase operator to the qubits 2 and 3. So with this code that you can, maybe if you didn't have it, just try to copy it for later. I'll leave it here a second. We can see that with this circuit, this is what it looks like. So as we said before, this is the, sorry. So this is the circuit how it look like. As we said, we have the C0 from register A to register B, bit by bit, and then this exponential of the projector on the 0 operator that is sustained with 2 axes and one phase. This is like how the circuit should look like. So moving on with the notebook, we can actually like define a graph problem. So let's define all the same, the one that I propose you here. And so we just need to like execute this cell, and we will obtain the graph of the problem here. So you're gonna need network X. So if you don't have it, pip install network X. There is a really nice library for graph problems. And so once that we have this problem that we want to solve, so we want to solve the max forecut problem for this 8 vertices problem, we can define our cost circuit in this way. So we define the max forecut as the class related to the graph G that we just define, and calling the method create circuit, we can output how the circuit for our problem looks like. And here we can see that is a pretty big circuit composed by 16 qubits, because we have 2 qubits per vertex times 8, the number of vertices is 16, and each of these blocks actually is a 4-qubit operator that here is not like output, but it can be like transpile on whatever basis you want. But the structure here, we can see that, for example, here we have this gate here is a 4-gate operator that apply the edge from, this is vertex 0, vertex 1, vertex 2. So this is the edge circuit related to the edge from 0 to 2. So this like class, what it does is just like append for each edge of the graph, the circuit we just defined. And this is the result. a really big, not nice circuit. But we can define our QAOA instance and try to solve this problem, in this case, locally. So how we can do this? We will begin our algorithm in the initial state, that is the plus state. So the equal superposition of all the possible binary string or computational basis state, yes. I mean, if we have like the all-to-all connection, we can just calculate it, because each of these circuit, edge here, operators, has this form. So the depth is just like the depth of this circuit times the number of edges. Then there is like the fact that we can parallelize a lot of them, but that's kind of depends on the sparsity of the graph. So the more the graph is sparse, the more it's going to be easy to parallelize some parts. But yeah, in principle, you can expect some depth that depends on the graph. I hope this is a... Okay, so yeah, we can define our QAOA instance. The QAOA instance must take in input a initial state, a mixer operator, and a phase operator, and a classical optimizer. So in our QAOA, we're gonna import different things like the QAOA, the initial state plus, they will be like, we'll prepare as initial state the plus state. From the mixer, we're gonna use what is called the X mixer, so the rotation along the X-axis that we were discussing before. And as optimizer, we're gonna use the gradient-free optimizer Copila, because it's good enough and we don't need so many iterations to make it converge. So defining some settings for the optimizer Copila, that is gonna be the max number of iteration, the tolerance, and this rowback that kind of is related to the initial change of parameters to like sample the landscape. We use this optimizer with these settings, and we define the QAOE class with the initial state plus. The problem is going to be the problem that we define before defining each edge, and the mixer, the X mixer. So running this cell and this cell, we can plot how the landscape look like. So this is like something that you can run right now, just running this different cells, because we are not adding any personal circuit. And so like if you run this QAOA, this is what you obtain. Here we have the range between 0 and pi for gamma and beta. And we have this structure where we have 2 minima and 2 maxima. Actually, what is gonna like happen is like this problem is for the beta space is gonna be symmetric. So actually, it's gonna repeat every pi over 2. So actually, this maxima and this minima and this maxima are the same as this one in some way. But this is how the landscape for p equal 1 look like. If you want, here you are using the sample cost landscape function. You can change even the range from 0 to pi here, but you can try to play a little bit with whatever you want. And 20 here is like the number of samples that we're using. So we want like a high resolution image. We will have just to increase this sampling number here. So both for gamma and beta. So if you want to have fun, you will find out that this is going to be like periodic in beta, but not in gamma. And so what we can do is just like we can optimize for the layer p equal 1 and see what like the optimizer does in this space, the classical optimizer and the VQE. So yeah, you can execute directly this cell here, and what you're gonna obtain, it's gonna be really kind of quickly, but I just show you, and you can check if you have the same result. If not, you probably like miss one gate of the definition of the edge set. But this is what happens. Here we can see like how the optimizer that begin in the white dot as optimize step by step. So it was already kind of like starting in the minima, because we decided to take in this package, like to sample with a grid this landscape and begin with a set of parameters that is like the minima of the grid. So the minima of the grid is achieved in this point, but actually is not the minima. We should move a little bit like on the left here to the red point. But this is exactly what like the copula does. The classical optimizer will start to move in this minima, looking for the global minima. And this global minima is at the value of minus 10.8. This is good. So we kind of can see like how the classical optimizer try to move in the landscape. Now we can try to like run this algorithm out to like with multiple depth, with multiple layers. So incrementing the depth, what we will expect is that this algorithm will increase the approximation ratio. So like the output is going to be better and better the more layers we use. So yeah, you can run this cell too. That it will take some time because we will have to run with different depth this circuit. So I let you like run it and have fun. Someone I think asked if we need the plot function. Actually, in the exercises notebook, it's the last version. So if someone like downloaded some time ago, it's not like that. Yeah, there is not like the plot function anymore. In fact, is being changed to this, where like if you don't have this the def plot E and plot landscape, you should download the last version of the outbook that I think Tor has put uploaded. So probably Francesca was the one that was asking this, and probably maybe has used the old version, Federica. Sorry. Yeah. So yeah, in the last version of the notebook, actually this problem doesn't appear because I try to remove the plot function .py file. I'm sorry for this.
Maybe I'm jumping on this issue a bit late, but was the plot functions.py problem resolved?
No, because like I make you upload another version where I just avoid to use that file.
Aha.
And I think maybe Federica has downloaded the old version. Could be. I don't know.
Be.
Because like the last version is the one here on the GitHub repository that don't use the plot function thing.
Mm-hmm.
No, it was actually in the page of the Jupyter notebook in which we are working now. So actually, I think that the old version was loaded, but it's not a problem. Like we can just download the file and upload it without. I think it's not going to take too much time, so it's okay.
Okay. Sorry for this.
So the notebook is updated in the lesson repository.
Yeah, okay.
But we don't know exactly when the latest pull was done on Helmi.
Okay.
Could have been a lag there.
Okay. But yeah, so I try to show you the results. Well, now I wait a little bit for someone like Federica that is trying to solve this problem. Okay, so let's move on and like execute the case where we optimize up to layer 5. Here you can even choose whatever number you want, up to you, but it's gonna take some time. So like the more layer you put, the more it's gonna take time. And here's the result. So actually we can see like how the performance for this problem increase layer by layer. And actually we will expect this to converge to like the optimal solution after a certain amount of like depth. So this is like, if we want to compare this result, for example, with the optimal, with the approximate algorithm from Guzman-Williamson, actually, in that case, the approximation ratio for the k=4 case is like 857. So is around 857 would be something around here. And actually, the performance for the QAOA is better. But this could be because like the graph maybe is like simple. So maybe even the Guzman-Williamson will output a good solution better than 8.5. So 8.5 is the worst case scenario. Okay. So yeah, was the first like part of the hands-on about the max forecast. And now I would like to discuss with you the case when k is not a power of 2. So if everyone has plotted this performance respect to the depth when you're in, you can start. Okay. So let's discuss the case when k is not a power of 2. So when k is not a power of 2, it's going to be a little bit less trivial to encode this problem on a quantum computer, because we will have to do with like some ambiguity or like some constraints. So let's begin with what I call the degenerate color method. So let's suppose that the k is not a power of 2. So and we still want to use the full Hilbert space. So what we can do is like, let's take, for example, the k=3 case. So we have 3 colors, and we map again the first color in 0, 0. So we have 2 qubits as expected. The second color in 0, 1, and the third color will have some degeneracy. So we'll map this third color to 1, 0 and 1, 1. So every time that we measure 1, 0, 1, 1, we will consider this as the same color for that vertex. So in this case, we are using the full Hilbert space because we are using all the 4 computational basis states for a 2-qubit system, but we are encoding 1 color out of 3 in the 2 different computational basis states. Of course, like if we take like a slightly bigger number, like 5, there are multiple ways of encoding like this choice of like 1 color in multiple like computational basis states. But here I want to discuss the case where like the choice is we map the first k-1 colors in only the first k-1 computational basis state. So 0 in 0, k-2 to k-2. And the last color is encoded with a high degeneracy in all the remaining computational basis states. So as I said, this is just a possible choice. I just want you to do like the exercise in this specific case. So what happens now? Let's look at the k=3 case that is like a little bit more self-explanatory. In this case, we have that the edge Hamiltonian, instead of containing only 3 projectors, will contain 6 projectors. Why? Because we will have that the first 2 colors are easy. 0, 0, 0, 0, so first register in the color 0, second register in the color 0, and equally first register in the color 1, second register in the color 1. The third color instead will be represented by 4 projectors, because we can have that same color, same state, 1, 0, 1, 0, same color, same state, 1, 1, 1, 1, but even the case of like same color, different state, 1, 1, 1, 0, same color, different state, 1, 0, 1, 1. So as we can see, in this case, we have that the number of terms is not the number of colors, but it's more than the number of colors due to this like degeneracy. So in this case, the Hamiltonian, the edge Hamiltonian, will be written as sum of projector on the color I, tensor state J, where I and J represent the same color. So we have this equivalence class where like before, for the power of 2 was I, because there was no ambiguity. So like each color was only 1 computational basis state. Now we will take care of this in this way. So II, JJ, where J represents the same color as I. So the thing is like how we like implement the case of the exponential of h hat when the number of states is not a power of 2. So in this case, we have a projector on a space of dimension 6. So the problem is a little bit more interesting. So let's discuss about how, like in general, we can implement on a quantum computer the exponential of a diagonal projecting operator when the dimension of the projecting operator is of the subspace is more than 1 and is not a power of 2. So a diagonal square binary matrix that is a diagonal projecting operator is a matrix that has 0 entries everywhere except on the diagonal, so when I is equal to j, and some of this entry will be 0, some other entries will be 1. So that means that this projecting operator matrix will be a set of 1s in some positions on the diagonal and 0 somewhere else. So let's begin with the case of when the number of 1s on the diagonal is m, and this m is a power of 2. When m is a power of 2, what we can think about to do is like to look for a permutation of the computational basis that will map all the 1s in the first m elements. So before the permutation, the diagonal matrix was like a set of 1s and 0s in some positions. And the idea is like we look for a permutation that maps this matrix in a matrix where like the first m entries are 1 and all the others are 0. And this matrix is just identity tensor 0. So let's suppose that we can find this permutation. So this we can like find a way to permute the diagonal matrix in such a way. Then, as I said, in this basis, these matrix look like this. A projector on the 0 state for a set of n qubits that we call register A tensor the identity on register B, where B is a number of qubits that is equal to log m, and we said that m is a power of 2, and the number of qubits for the register A is going to be n minus the number of qubits for the register B. So let's try to understand who is this matrix here. The matrix here is exactly what I was saying before. It's like if we take the tensor product of a matrix that is 1 and the rest is 0 on the diagonal tensor, the identity, there is identity with the m by m, the resulting operator is a matrix that has the first m elements are 1 and all the rest are 0. The good thing about this is that we know how to implement the exponential of this part here. We know how to implement the exponential of the projector on the 0 state for a certain amount of qubits, whatever it is. So if we take the exponential of a generic projector for a space of dimension m power of 2, we are sure that we can write this exponential as projector exponential of the projector on 0, permutation related to that matrix, exponential of the projector on the 0 state, tensor identity, and of course, permutation back. There are questions here because I don't know, it was like a really wavy way of explaining this, but the idea is like we can which one is the permutation will not care in this in this session, but in principle this permutation exists because a permutation is a unitary operator and can be implemented on a quantum computer in this case efficiently. So we will assume that we can do this. And okay, so when it's not a power of 2, so let's suppose that m is not a power of 2, we can write m as a sum of terms that are powers of 2 and divide the projector operator as a sum of matrices, which each matrix has a number of 1s, or the subset of the dimension of the space is a power of 2. The good thing about this is that if we want to implement the exponential of gamma, so these are all diagonal operators, so we can write this as a product of the exponential of the singular gammas. So each gamma is a matrix that projects on a space that has a dimension that is a power of 2. So actually, we kind of find out a way in general to implement this exponential. So now I will try to like show you that like this is possible for the case of k equal 3. And actually, it's not so even hard. So we said that like in this case, the case of k equal 3, with this degeneracy of the color, we have that the projector operator project on a space of dimension 6. So 6 can be written as 2 to the power of 2 plus 2 to the power of 1. So the idea is we divide the Hamiltonian in a sum of two terms, h1 and h2, where h1 will correspond to a space, a projector of dimension 2, and h2 will be a projector of dimension 4. And then we just like implement the exponential of this as the exponential of h1 times the exponential of h2. So let's suppose that h1 represents the first two colors, 0, 0, 0 and 0, 1, 0, 1. So it's going to be the projector on 0, 0, 0 plus the projector on 0, 1, 0, 1. And the second Hamiltonian will be the projector on the third color, so all these four states. I will try to like maybe show you that this can be done if I use the whiteboard is okay. Maybe I can do the calculation on the whiteboard if you see. Just to like I want to show you how this can be done because the exercise after is gonna be trying to use this. Yep.
Change the camera actually.
A good idea. I don't know. So let's take H1. H1 we said that is the projector on 0, 0, 0 plus the projector on 0, 1, 0, 1. So the idea here is that we want to write this as a permutation times some projector tensor some identity and some permutation back. This is like what we want to do, what we want to achieve. So here the idea is like if we apply the C0 gate from 2 to 4 to H1, so what we obtain here is that the zero state, this is going to happen like term by term. So the first term, see x to 4, 0, 0, 0, 0, 0, 0, is going to remain the same because the first qubit is in the zero state. Sorry, the second qubit is in the zero state, so no operation will be applied. So this is going to be itself. You see it from there in some way? Okay. The second term instead is going to be influenced by this C0 gate because we apply C to the cat and C to the bra. And in this case, we have the second qubit is in the state 1, so we will apply the X operator. So we're going to flip the fourth qubit. So the resulting state is 0, 1, 0, 0, 0, 1, 0, 0. Can you see this or not? Yes. So then like if we do this change here, what happens is that the resulting is the sum of this term and this term here. If we look at these two terms, they have the first, the third, and the fourth qubit in the state 0. But like the two states, the two projectors. While the second qubit can be whatever. So actually, like explicitly, this should be done like this. This is the first state is 0, tensor 0, tensor 0, tensor 0, tensor 0, plus here we have 0, tensor 0, tensor 1, tensor 1. For example, tensor 0, tensor 0. So we can see that like we can group this term, this term, this term, and this term, this term, and this term. Can you see this? So then the sum of these two terms is 0, 0, tensor. Here we have 0, 0 plus 1, 1. This is an identity. Tensor 0, 0, tensor 0, 0. So we end up that if we apply the CX, the CNOT gate from qubit 2 to qubit 4, this projector is equivalent to 0 tensor identity, tensor 0, tensor 0. That is exactly the form that I was trying to show you before. So it is this type of form here. The thing is, like, if we look at the CNOT operator, the CNOT operator is a matrix that looks like this. And this is a permutation of the computational basis. So we have found like that in this computational, in this way, we can write the first term as a permutation that is in this case correspond to the CNOT from qubit 2 to qubit 4 time a projector on a register of the 0 state tensor an identity. This is exactly this claim here. So this is good. One thing that I forgot to tell you is like every permutation operator can be implemented in terms of using only X gate, CNOT gates, and Toffoli gates. So actually, this is exactly what is looking like. A similar like strategy can be done for the H2. In the case of the H2, we have these four states. So if we apply, we flip the first and the third qubit and do some calculation in the same way, what we obtain is like this H2 can be written as a permutation because X1 times X2 is a permutation of the computational basis times a projector on the 0 state for the qubit 1 and the qubit 3. So this means that when we will exponentiate H1 and H2, this is what the circuit how will look like. The green region corresponds to the exponential of H1. In fact, we have CNOT gate from 2 to 4, multi-control phase that correspond to the exponential of the 0 projector on qubit 0, 1, 0, 2, and 3. So we have control phase. And then, of course, CNOT back. While H2, the exponential of H2 will be just a control phase operator. So we have found a way to decompose the edge operator H hat in a sum of two terms, and we know how to implement the exponential of the singular terms of the sum. So what I want you to try to do now, and I know it's not going to be easy even because last year we were having tables. This year there are no tables, so like do pen and paper exercises is not a good idea. But the idea is like on the Jupyter notebook, I would like you to like try to implement the case when instead of like here we have divided this set of states as these two represent H1 and the last four represent H2. And I will like you to try to do on the notebook the case where we have the first four represent H2 and the last two represent H1. So a different partition of the problem. I think it's gonna be hard to like do it without pen and paper, but yeah, this is like kind of the idea. So can try to understand how to do this H1 plus H2 when this is H2 and this is H1. If you look closely, this is something that we already have seen before in the slides. So the only problem is trying to like implement this. So trying to like do similar calculations. Grande Armando. Good. And so yeah, this is gonna be the exercise for now. So here I'm gonna leave you with some time. I hope the exercise is clear. If not, I try to re-explain everything in detail. I hope you didn't lost you everyone, but I don't know. Well, I try to give you one hint for the H2 and then try to leave you for the H1 and then in case I give you both. But like if we take the H2 is something that we already seen. Because H2 is the case of like 0, 0, 0 plus 0, 1, 0, 1 plus 1, 1, 1, 1 plus 1, 0, 1, 0. So this is the case where the first register and the second register are the same binary string. So this is exactly the max 4-cut part of the Hamiltonian. So actually, the thing is like, as we say, this is actually the max 4-cut, so we just need to implement the same circuit because we can rewrite this. So this is sum over I, same binary string. For register A and register B, this can be written as C naught from A to B identity for register A, tensor projector on register B. So written in general, this is gonna be Cx, let's say 1 to 3, Cx 2 to 4, identity tensor 0, 0, 0, 0, Cx 1, 3, Cx 2, 4. So we can see again that for this operator, we have a permutation and a projector on the 0 state. So this is exactly what I was showing before. For the last two, it's kind of similar how we can do this. So yeah, maybe I give you 5 minutes to think about it, and then meanwhile I go to the bathroom. So H1 is the projector on 1011 plus the projector on 1110. So here we have a space of dimension 2, so it's a power of 2. And we can see that if we apply again the C0 gate from the qubit 2 to the qubit 4, what happens is we end up with 1, 0, 1, 1. Sorry, if we apply Cx H1, Cx 2, 4, we end up with the first state is like the qubit 2 isn't 0, so we'll not do anything. While here the second qubit is going to be in the state 1, so we'll flip the fourth qubit. So it's 1, 0, 1, 1 plus 1, 1, 1, 1, 1, 1, 1, 1. So in this case, we can see again what happens here is that the first qubit, sorry, these are bracket. The first qubit and the last two are in the same state, and the second one, who cares? So this is projector on one, tensor identity, tensor projector on one, tensor identity, tensor projector on one. So if we apply x1, x3, x4, so we apply x1, x3, x4, this become again 0, 0, tensor identity, tensor 0, 0, tensor 0, 0. So in this case, the permutation is x1, x3, x4, cx from 2 to 4. And again, we have, this is the projector. So I hope in some way this is clear. What we have to do now is to get back and share. Oh, okay. Next time, if it will happen. But yeah, if we go back to the notebook, the idea is going to be to try to implement this circuit, for this case, in this case, for a max 3 cut. So we're going to have a max 3 cut case where the number of nodes is going to be 2, and we're going to map the color 1 in 0, 0, the color 2 in 0, 1, and the color 3 in 1, 0, and 1, 1. So we have this degeneracy that I was talking about. And then we will have to define on the module create edge circuit, the proper circuit that represent this operator. That actually will look like this. So where we use I use a simplification here of the circuit, because actually, if you remember the structure of the circuit, there was a C naught from 2 to 4 for this is the exponential of H2. But there is another C naught from 2 to 4, even for the second term, so it cancel out. So yeah, I don't know if if you want to copy the circuit, here it is, and you can try to simulate the max cut for a 3 cut problem using this specific encoding. I leave it here for a little bit, but yeah, I hope you get something out from this. Okay, so now maybe I'll move on. So if we implement the circuit, this is how it looks like, where I apply some simplification of the circuit because the C naught for like the max 4 cut was with another C naught here, but this gate here has another C naught that simplifies. But if we run, in this case, the QAOA for as before, where we use as initial state the plus state, as problem circuit, the one obtained from this edge definition applying to the graph G of before. And as a mixer, we use the X mixer and optimizer, again, the Cobila. We obtain, in this case, a slightly different optimization landscape respect to before, because the problem has changed. So the Coste-Hamiltonian has changed, and even the phase circuit has changed. So, but again, in this case, we have that the problem in this region has like a big minima, a big maxima, and 2 small local minima maxima. So actually, it can happen that like our optimizer, if it starts in a random point, for example, if we start the optimizer from here, maybe we'll get stuck in this local minima. But actually, the best minima is this one, and we find it with a value of minus 972. So if we run now the case of depth equal 5, we can see again what happens is that incrementing the number of layers, so the expressibility of the ansatz, we can achieve a better performances for the max 3 cut problem, and it seems to like converge to like the optimal cut of 1. If you want to try to put like more layers, you're free to do that whenever you want. But now maybe the time is starting to like to be not enough because we just missed the last method. So I come back to my slides, and we can discuss the last method that I want to like propose you. And this method is, instead of like encoding one color in multiple like states, we can encode like instead of using the whole Hilbert space, we just use a subspace of the Hilbert space. In the sense, let's suppose that we encode the three-cut problem, first color in 0, 0, second color in 0, 1, and third color in 1, 0. So we left out the 1, 1 state. What we want to do is like what is called a constrained QAOA, where we explore only a constrained space. So just a subspace of the Hilbert space that is enough to encode the problem. So let's suppose that we define the feasible set of states as the span of BK, where BK is the first K elements of the computational basis. So now what happens is that what we will have to do is kind of like try to properly define the QAOA. But in the QAOA, we have three ingredients. The first one is the initial state. So we will have to choose a proper initial state that is in the space that represent the colors. So what it could be like a good initial state for the max three-cut case in this setting is the equal superposition of 0, 0, 0, 1, and 1, 0. So leaving out the 1, 1. The component of the vector for 1, 1 should be 0. The other thing that we have to do is define a proper constraint mixer. So the mixer operator must mix states only that represent colors. So then we will have to like define proper like constraint mixers, and this is like kind of the interesting part, because the phase Hamiltonian, instead like the phase circuit, instead we said there is a diagonal operator. So this means that preserve the feasible subspace. So if we apply a diagonal operator to a linear combination of computational basis state, it will remain as a linear combination of those computational basis states. So what happens here is like, if we decide to use this strategy, so use not the whole Hilbert space, but just a subspace of the Hilbert space, as cost function, we will use exactly the one of the k when k is a power of 2. Because the Hamiltonian in that case is 1 when the two colors are the same. So that is enough even for this case. So let's start by defining what is a constraint QAOA. So a constraint QAOA is like a quantum alternating operator answer defined on a feasible subspace B. So let's take B as a span of some capital J computational basis set J. And this set J represents some binary strings. So then we have to define what is a valid mixer. A valid mixer is a unitary operator that depends on one parameter such that preserve the feasible subspace. So that means that when we apply this mixer operator with whatever beta we choose to a state that is feasible, the resulting state is still in the span of B. This is a really intuitive like condition for a mixer to be valid, also like to be employed in a quantum alternating operator ansatz. And the other condition that we should require is that it provides transitions between all pairs of feasible states. So that means that if we take two computational basis states x and y in B, and there must exist a parameter beta star and an iteration number r such that if we apply enough times this mixer operator, the overlap between x and y is not trivially 0. So these are the two conditions that we must like ensure for a mixer to be valid. So let's see two examples of mixers that are valid. In the unconstrained case, we have that the unconstrained case is a constrained case when we use the full Hilbert space. An example of valid mixer is the X mixer, the one we already used. This X mixer, as we said before, is just like rotating each qubit of a parameter beta 1 along the axis X. This mixer here is valid, yes, because it preserves the feasible subspace, because all the feasible subspace is the whole Hilbert space, and in particular provide transition between all pairs of states. In fact, let's take the mixer, the X mixer for beta equal pi over 2. this is like the formula related to this operator here in the 3-qubit case for pi over 2. And we can say that like it contains all the sum of all the possible bit flips. So bit flip of first qubit, second one, third one, double flip, bit flip, and three bit flips. So that means that if we want to evaluate this formula here, where we choose whatever computational basis state y we want and whatever computational basis state x that we want, the overlap, or for example, beta equal pi over 2, will not be 0, but will be 1 over 8. So this like ensure that this mixer is valid, because it provides transition between all pairs of states, because each computational basis state is related to another one by some bit flip. 0, 1 is connected to 1, 0, flipping both qubits. Okay, and then we have the example for the constraint case is the Grover mixer. The Grover mixer is not the only possible like mixer that can be defined on a constrained space, but it's something that we can achieve right now because it's based again on the idea of using a projector. So let's suppose that we have a unitary state preparator, so a quantum circuit US that starting from 0 is able to prepare the state F, where F is the equal superposition of all the feasible states. So this is 1 over square root of the dimension of the space, the number of states in the constraint space, sum over I in B, sum of E. So this state is the equal superposition of all the feasible states. The Grover operator, the Grover mixer operator, is defined as the exponential with the parameter beta of the projector on the state F, where F is this equal superposition of all the computational basis states that are feasible. So here again, we can see that we have, this is a projector on a space of dimension 1. So in some way, we can relate this again to the projector on the state 0. How we do this? We have this state preparator US. So the thing is like, as stated in equation 34, we can write this exponential as US, state preparator, exponential of the projector on the 0 state, US dagger. So the only thing that we need is to be able to prepare the equal superposition. And the circuit, in this case, will look like this. So US dagger, this is again the circuit for the exponential of the projector on the 0 state, US. So I hope like you kind of know what like this formula here that works. So when we take the exponential of a basis change, that is US U dagger, you can take it out. And what I would like you to do is again another pen and paper problem, is like try to prove that this operator, this Grover mixer, is a valid mixer. So trying to prove that with this formula here, or this formula here, maybe it's easier, both it preserves the feasible subspace and provide transition between all pairs of feasible states. So this, yeah, this is like what I would like to do, but like with the time, at what time we want to kind of finish, Tor? It's like 3 hours.
Let's go on for 3 more hours.
Yes.
No. So we had promised to be at Albanova University Center at 17:30.
Okay.
It takes 10 minutes to walk. So in principle, you can go on for 20 more minutes, but we also maybe need to stretch our legs and visit the bathroom and I don't know.
Okay, okay. So maybe I just move on here. I just like this part of exercise. I just like kind of tell you. So yeah, we want to like try to understand if this formula related to a valid mixer, we just have to understand if preserve the feasible subspace. So if we input a state that is feasible here, the output is going to be the vector itself plus the projector, the projection of the vector along F, and then F vector. So it's going to be feasible. If like maybe I do the calculation on the board there. Yeah, let's do this. So I stop sharing here. Oops. Okay, so we have defined the Grover operator as the complex exponential matrix of f that we can rewrite using the projector formula as identity plus e to the I beta minus 1 ff. Good. So the first property is to be preserve the feasible subspace. So this means that U Grover apply to a vector V must be in the span of B. Now it's like you super confused, so it's gonna be pretty shitty even from home. So we just like to plug this in this formula. So this is equal to V plus e to the I beta minus 1 f v f. So it's a linear combination of f and of v and f. So this is in the span of B. So the first condition is already verified, just like plugging, like applying the Grover operator to a generic vector in B. The second condition is must provide transition between all pairs of feasible state. So this means that x, u, y is greater than 0. So let's see. Let's take x and y and write f. It's really confused. So let's plug here this operator here. So identity plus e to the I beta minus 1 f y. So we can see that what it remains is the scalar product between f and y that is different than 0 along f. So the first term, sorry, is like the identity. So it's like x, y. So this is like related to the first term of the sum. The first term is just like the identity, so it's like the scalar product between x and y. The second term related to f projector is e to the I beta minus 1 x f f y. So this term here is for all the choices of x and y is not 0 because f is the equal superposition of all the feasible states. So this is like actually equal to 1 over the dimension of the space. So for all the choices x and y, this property is verified. So actually the Grover mixer is a valid mixer. That's good. If not, we will not call it mixer. But so now we know why this operator is it's valid, and we can use it for a constrained QAOA. So if we look at the again at the code, this is like, for example, how will look like in the case of a max 3 cut. And the max 3 cut case, what we do is just like we prepare the initial superposition of all the first 3 qubit states, and this can be achieved in this way. And then let's suppose that we have 3 nodes. So we just tensorize this structure. If we want to prepare the Grover mixer for 3 nodes with 3 colors, this is how the circuit will look like. We prepare for each vertex of the problem the equal superposition of the first 3 colors, and then we apply the exponential of the 0 state, that in this case is a multi-control phase gate. And if we want to measure how the overlap with 2 generic states look like, this is a plot. So this is the plot of like the second property of validity of choosing x and y to be 2 states. and changing the range of beta from 0 to pi. And we can see that like there are some beta where the overlap is not trivially 0. So this means that for the choice of x and y that I made for this specific part of the code, the overlap was not 0. So like we prove numerically the property of validity for the mixer. And in fact, just to go back, it's funny to like try to like understand this mixer from another perspective. There is a graph perspective. So we can actually, all this mixer that we have been like working on have this structure. They are exponential of a certain Hamiltonian. So they can be obtained by exponentiation of a certain Hamiltonian. And this Hamiltonian actually is, for example, in the X mixer case is like x1 plus x2 plus x3 in the 3-qubit case. So and in the Grover case is like just the projector on the superposition of all the possible states. The idea here is like that we can interpret this Hamiltonian HM as an agency matrix. So for example, if we plot on the computational basis state, the representation of the matrix will look like an agency matrix of a graph. So actually we can relate the valid to be mixer to require the Hamiltonian, the agency matrix related to the Hamiltonian is connected. So for example, here we have this matrix here for a set of like computational basis states that provide transition between some pairs of these states. And we can see that this agency matrix here is related to a graph that is not connected. So what happens is like if we choose as Hamiltonian, the Hamiltonian that kind of like does this operation, and we exponentiate that Hamiltonian. What happens is that like the parts that are not connected will remain unconnected. So there will not be transition, for example, from this state Zi to the state Z2. So there is like, this is something that we will not do in the exercise, but in this way we have a new like tool for understanding how to design mixers for constraint optimization problems with some like graph analogy that works really well and tell us how like the transition will be obtained. And here, for example, we have the representation as an agency matrix of the X mixer. So the X mixer for a 3-qubit case is like x1 plus x2 plus x3, where like x1 represent the flip of the first qubit, x2 the flip of the second one, and so on. And if we represent the matrix, it looks like this. So this is an agency matrix. And the agency matrix related to this graph is an hypercube. So actually what we're doing is like using an hypercube to provide transitions between all pairs of feasible states. This is something like, at least is funny to see, because the Grover mixer instead is a complete graph, because we have this is like the matrix associated to the projector on the feasible subspace, on the feasible state F, and this agency matrix is actually the agency matrix of a complete graph. So this is like a way to like see graphs in a different way. But we will just move on because we don't have so much time, and arrive to how to define the max k-cut in the case of the constraint. So what we have to do, first of all, is like to begin in an initial state that is feasible. And we know that like, let's suppose that we have a k-cut problem, and we are able to prepare on one vertex the equal superposition of all the possible colors. Then the equal superposition of all the possible configurations on the graph is just the tensor product for all the vertices of this state. So once that we have US, the state preparator that prepare the equal superposition of all the possible colors for one vertex, the equal superposition of all the possible color partitions of the graph can be obtained just like taking the tensor product along all the vertices of this state F. So actually we can prepare this state just independently vertex by vertex. So kind of in this way here, where this state, for example, represents the equal superposition of all the possible configurations on a 3 vertex graph of a 3-color case. So going back to the slide, this means that we can use this to implement a grover. So the grover mixer in this case is gonna look like this. We just prepare the equal superposition of all the possible partitions of the graph times the projector on the 0 state. So the grover mixer for this constraint problem can be defined in this way. So the total cost of implementing this kind of mixer is 2 times V, where V is the number of vertices, times the cost of implementing the initialization for that specific sum of all possible colors, plus the cost of implementing this operator here. This operator here is a multi-control phase operator that entangle all qubits in the circuit. So we have to implement a V times LK minus 1 control phase operator. This is a kind of a big operator to implement on a quantum computer. So what I would like to propose you, instead of implementing this grover operator, is to try to implement the tensorized version. So instead of like do this operation on the whole space of all the possible partition of the graph, do this just like vertex by vertex. So instead of we take the fact is like each vertex is independent from the other. So we use as mixer this operator here that is like I prepare the grover mixer for each vertex. This is like for the grover mixer for one vertex, and just apply independently for all the different vertices of the graph. I hope you can see the difference between taking this and taking this. The main difference is that in one case, this is the full Hilbert space where we look on multi-control all the qubits for a phase gate, and the other option is a structure like this, where we have the grover mixer vertex by vertex. So this is in terms of like cost, in terms of C0 operator, for example. So in terms of efficiency of the circuit, this is like way easier to implement on a real quantum computer, and we'll have like less noise. And in any case, will even work because we have to check it is a valid mixer. Actually, from the graph theory from before, we have to check that the graph associated to this mixer is connected, and take the tensor product of different mixers correspond to take the the box product or core Cartesian product of the agency matrices of the two mixers. So this is like if I have the agency matrix G and the agency matrix H, or equivalent graph, taking the box product correspond to taking G tensor identity plus identity tensor H. So the good thing about this is that this operation, if preserve connectivity, so if we have G and H are connected, G box H is connected too. So we are sure that this graph is connected to. It's just not the complete graph, it's the tensor product of complete graphs. And at the end of the story, we have a good constraint mixer. So we can in some way summarize this as the cost circuit that we're gonna use is the one of the power of 2. The mixer is gonna be this Grover mixer that I just defined, and the initial state is gonna be prepared with the gate US. So just to conclude and show you the results, here we're gonna use, as I said, this kind of like Grover, and when we run the circuit for the constraint case, we can have like is a kind of like more complex landscape respect to the cases of before, but we can still like optimize it. And when we run it up to depth equal 5, here we compare in blue the case of like the degenerate color. So when we use all the Hilbert space and define a proper coast circuit. Respect to the orange one, that is when we use this constraint method. And we can see that in this case, seems like outperform like in each depth the other method. So I was super quick here, but was needed. And yeah, that's kind of all. I leave you here with some references about this work. And for the Gosman-Williamson algorithm, check out Wikipedia. There will be enough.
Very good. Thank you very much. Been a long day. I'm not sure if anyone's brain is ready to ask a question. Yes? One brain in the audience?
Very related to the very beginning of your slides, where
Yeah.
you had to compare Copila and SPSA.
Yeah,
gradient
like this,
descent.
just like this plot here.
Yeah. So you can use them just to double check for QAOA and VQE as well, right?
Yeah, yeah.
Okay, great. Then, just briefly, when to choose each one.
Oh, it is like kind of like as a choice what you will choose. It's hard to like get a proper response to that because each of those have different like methods. But like for example, for noise, like the stochastic gradient one seems to work better under like noise conditions. So if you're like trying to run this on a real quantum device, using for example one that uses the exact gradient or some like weird tricker like machinery, sometimes under the noise doesn't work. While for example the SPSA seems to work better under noise conditions, but need a lot of like evaluations. So you will have the cost of like taking a lot of evaluations. While for example, if you have like low noise conditions, using the gradient descent technically will be good enough. But here we use the Copila because the Copila is able to converge in a small amount of steps for this problem. So the choice is really like user-based. It's like there is a lot of literature trying to claim that some are better in some conditions, some are better in others. And I don't know exactly which one I will recommend you for this.